Hello and welcome back to another A-level maths revision video. So I hope you're doing amazing on this bright and sunny day. If you're not, for whatever reason, then hopefully this mock exam paper here might just cheer you up, right? So as we can see then in the bottom left corner here, this is mock paper set D, paper 1. Now, before we jump into the paper here, there's a few bits of information that we do need to run through, as always, right? So let's quickly read through all of the waffle here, then we can jump into the paper, right? So this practice paper here closely follows the Pearson Edexcel specification for A-level maths, but Pearson Edexcel have no affiliation to this paper, of course. You can just use your formula, but that's absolutely fine. You can also just use a calculator, again, that's absolutely fine. And as always, then you do get 2 hours or 120 minutes here to complete this examination paper. Now for this video and this mock exam paper here, as you can see then there are 14 questions in total, with the total number of marks for this paper being 100, as you would expect for any regular A-level maths exam. The rest of this here is just the standard kind of waffle that we don't really need to read through, so that's absolutely fine, right? Now this paper here, as we already mentioned then, this is set D, paper 1. So this is part of the 2026 A-level maths predicted paper series over on our website, AJMaths.co.uk. If you would like to have a go at the paper as an actual download, then that is available to our members over on our website. So by the time that you're watching this video here, it will already be up on the website. So if you're a member, go and download it, give it a go, let us know how you get on. If you're not a member and you would like access to the paper, then feel free to become a member over on our website. At the moment, we are running a deal here with the with the code revision. I'll leave that in the description down below. So that is for 20% off. So go and grab that. It's a limited time deal here to get access to all of our predicted papers. At the moment, there are 10 predicted papers already up on our website. And there'll be another 2 added shortly for paper 2 and paper 3 for this examination series. You can also become a member as well on our YouTube channel. So the highest tier, the support tier, does give you access as well to all of our predicted papers for A-level maths and A-level further maths. So again, you can access the predicted papers. I can't speak anymore. You can access the predicted papers via that way as well. Just drop us an email at support@ajmaths.co.uk with your YouTube username, if that's how you've accessed the predicted papers as well. I'll send all of those over very, very shortly. But other than that, there isn't really too much to kind of go through here. Standard stuff, right? 14 questions, typical layout of a paper. So I don't want to waffle for too long. I think that covers absolutely everything here in terms of an introduction. Other than that, I just want to wish you the best of luck here with paper 1 next week. And yeah, that's enough for the waffle. I don't really know what I'm saying at this point here. So let's just get started then with question 1. So to get us started here then, question 1, as we can see on the screen here, right, is based on logarithms. So what are we given then? So what we're given here is this logarithmic equation. So 2 log of 5 minus x minus log of 7 minus x is equal to 0. What we want to show then is the following here. So for part A then, where do we begin here? Well, let's just start with this logarithmic equation here. So to begin with then, I will use the power rule here and bring the 2 up as a power. We get log of 5 minus x there. That's squared, bringing the 2 up as a power, minus then log of 7 minus x here, and all of this is equal to 0, okay? Now at this point here, we have a difference of logarithms here, right? So what we can do then is express this as a single logarithm. So we get log of, so for the numerator here, that is this, right? So 5 minus x all squared. So 5 minus x all squared. That is all over then 7 minus x. Like so. And this here is equal to 0. Now, for the next step here, we now want to get rid of the single logarithm here. That's this logarithm on the left-hand side. How do we do that, I hear you ask? Well, what we do then is we express the left-hand side and the right-hand side here as a base of 10. So what I mean by that then is we would write this as 10 to the power of this logarithm here. And then on the right-hand side, that would be 10 to the power of 0, right? So on the left-hand side, the whole point of doing this is that they cancel. So the log just disappears and we just get left with this here inside the bracket. So we get 5 minus x all squared. That's all over 7 minus x. And on the right-hand side here, we get 10 to the 0, but anything to the power of 0 here is just 1, right? So we can just write that as 1, okay? And we're looking to obtain this here, so let's just keep going then. For the next step here, let's just get rid of this fraction. So times both sides by 7 minus x here. We get 5 minus x all squared is equal to then, so it's 1 times 7 minus x. That's just simply 7 minus x there. Now expand these double brackets here. Feel free to write this as a product of double brackets, or you can just do it off the top of your head. Just please don't make a mistake. So we get 25. I get minus 5x and another minus 5x in the middle, so that's minus 10x. And then finally plus x squared there. And that is all equal to 7 minus x. Good stuff. So we're pretty much there now. They want this here. I've got a 7 here that I need to get rid of and a minus x. So let's just subtract 7 and add x to both sides here. If we do that then, what do we get? So we get x squared. So we've got x squared. I've got minus 10x plus x then. So that is minus 9x, right? Perfect. And then 25 minus 7. That gives us plus 18. And all of this here is equal to 0. And just notice then, this is exactly what we wanted here for part A, right? So as required there, happy days. So as required, and let's just give that a smiley face. We know we've got it correct. Perfect. So that's the first 3 marks there in the bag, nice and easy. Now for the next part of this question here, part B, we've got 2 parts to this, right? So let's just start then with part 1. So for B part 1 then, it just says find the roots of x squared minus 9x plus 18 is equal to 0. Nobody watching this video here should be struggling with this. This is basic GCSE maths. It's actually foundation, just factorizing this here, right? So this does factorize, as we just said then. So we can write this as double brackets. We get x minus 3 and x minus 6, okay? And this here then is equal to 0. From here, we get 2 roots or 2 solutions. So we get x equals 3. So x equals 3. And the second solution here is x equals 6. We've got this solution here and this solution here. Nice and easy, right? As I said, nobody should be struggling with this. If you are, it's not looking good, fam. And then for B part 2, it just says, state which of these 2 roots is not a solution of this logarithmic equation here, clearly stating a reason for your answer. So basically, if you just consider these 2 solutions here, which is a problem? So if we consider then x equals 6 here, why would that be a problem? Well, go back to the original equation here. If you substitute x equals 6 into the equation, what happens? So this here is log of 7 minus 6, that's log 1. That's all right, that's not a problem. However, with this log here, that's 2 log of 5 minus 6. That gives me 2 log of minus 1. Now that is a problem. So what we say here is the root. So the root that is not a solution. The root that is not a solution. I apologize for my handwriting, by the way. So the root that is not a solution of this equation here, I won't bother writing it down. So the root that is not a solution, in fact, I'll just write this as, let me try again. So the root that is not a solution is, it's probably easier to write it, so x equals 6. The reason why then is because, so the root that is not a solution is x equals 6 because, as you can tell, I find English hard. So because, what do we get here then? So log of 5 minus 6 is equal to log of minus 1, which is undefined. Okay, which is undefined. And there we go. That's all we need to really say there. So apologies. Hopefully that did make sense there. What I meant for the very last part, English is much harder than maths. Okay, so there we go, right? That gives us the solution there to question 1. So moving on to the next question here, question 2. What we can see then at the very top here is we have the function f, right? So f of x is equal to the following, where a and d are just constants. What we're also given here is that 2x minus 1 is a factor of f of x here. So for the first part of this question in part A, we just want to show the following here. So for part A then, let's just do this at the very top. We want to show that a plus 8d here is equal to minus 14. So if we're given that 2x minus 1 is a factor of f of x. And what we know here by the factor theorem is f of 1 over 2 then is equal to 0. So if we substitute 1 over 2 into this function here, hopefully with a little bit of simplifying, we should obtain this result here, right? So let's just do that then underneath. So f of 1 over 2, that is equal to, so we get a times 1 over 2 cubed. So a times 1 over 2 cubed. We then got 5 lots of 1 over 2 squared. So 5 lots of 1 over 2 squared. Like so. I've got plus x's, that's just plus 1 over 2. And then finally plus d here. And all of this is equal to 0, right? By the factor theorem here. Let's just simplify them. What do we get here? So that's 1 over 8, so 1 over 8a there. I've got 5 times 1 over 4, so that's 5 over 4. Plus 5 over 4, plus 1 over 2, plus d, and this is all equal to 0, right? Now what they've got here is just a, it's a plus 8d, so it makes sense then to times through by 8, right? So timesing through here by 8. If we do to one side, make sure you do it to the other as well. So I get a, that's 5 over 4 times by 8. So that's the same then as 5 times 2, which is 10. So plus 10 there when my pen works. A half times a is 4. And then d times a is 8d, right? And that is all equal to 0 still. And this is perfect, right? Because what I've now got here is a plus 8d, exactly as they've got there. So a plus 8d. And then 10 plus 4 is 14, right? So if I subtract 14 from both sides here, this is equal to minus 14 as required there. Okay? So as required, happy days, we know we've got the solution. So we'll give that a smiley face. Perfect. Okay? So that there is a solution to part A. Now for part B then, let's just do that underneath here. We are now given that x plus 1 is also a factor of f of x. So what we want to do here is find the value of a and the value of d. So let's use this factor here again then. So if x plus 1 is also a factor of f of x, then what we know here, again, by the factor theorem, is f of minus 1 is equal to 0. And again, all we're going to do here is just substitute minus 1 into this function. So if we do that underneath then, what do we get here? So we get a, in fact, sorry, let me just write that fully. So I'm going to write this as f of minus 1 is equal to then, so it's a times minus 1 cubed. So minus 1 cubed plus 5 lots then of minus 1 squared. 5 lots of minus 1 squared plus x, that's just minus 1 there, plus d. And again, by the factor theorem here, this is all equal to 0. Okay? So let's just simplify here. Minus 1 cubed is minus 1, so that's minus a there. This is 1, so minus 1 squared is positive 1, so times it by 5, and I get plus 5 there. Why is my pen doing that? It shouldn't be doing that. Let's try again. So that's plus 5 there, as we just said, minus 1, and plus d, and that's equal to 0. So let's just simplify here. I've got minus a plus d. So 5 minus 1 is 4, but what I will do here is take that to the other side then. So subtract 4 from both sides. That's minus 4. Why am I doing that? Well, clearly what we're going to do here is form simultaneous equations, right? And from there, we can just solve those and find the value of a and the value of d. Nice and easy, right? So let's just do that up here. So we've got the first equation here from part A, which they gave you anyway. That's a plus 8d is equal to minus 14. And then we have the second equation here that we've just obtained, right? So that's minus a. So minus a plus d is equal to minus 4. So let's just solve these here. Nice and straightforward then. It shouldn't really be causing a problem, right? As A-level math students, I can just add these together. So they just cancel. Beautiful. 8d plus d is 9d. And then minus 14 plus minus 4 is just the same as minus 14 minus 4, giving us minus 18. So therefore then d here is clearly minus 2. Minus 18 over 9 is minus 2. Now that we find the value of d here, let's just find the value of a. We can use either of these two equations here. It's completely up to you. I'll just use the second one here. So minus a plus d, but d is minus 2 here. So minus a minus 2 is equal to minus 4. Add 2 to both sides, I get minus a is equal to minus 2. And then clearly here, a is equal to positive 2. Okay? So there we go then, right? We find the value of a and the value of d here. So a is positive 2 and d here is minus 2. Okay? And there we go then. So hopefully not too bad there. And that gives us the solution to question 2. Now for question 3 here, this is where things start to get a little bit more interesting, right? As we can see then for a part 1 and part 2, we do have differentiation. And then for part B, a little bit on integration, right? Which is certainly more interesting than the factor theorem and logarithms. So for a part 1 then, a part 1 here, we want to find this derivative here, giving your answer in simplest form for the first 2 marks, right? So if we're differentiating something like this here, so the derivative of a natural logarithm, this here, we take that as f of x. So the result here is equal to, so it's f prime of x over f of x. It's a fraction, right? So let's just apply that then to this here. So as we just said, the denominator here is just f of x. It's just whatever the argument is here. So let me just write down the full derivative here, just so it's a little bit clearer. That is d by dx of ln cos squared 4x. So that is equal to then, as we just said, a fraction where the denominator here is cos squared 4x, like so, just the argument here. And then for the numerator, we now differentiate the inside here, right? Whatever this is here. To differentiate this here, just apply the chain rule. Or you can just do it off the top of your head if it's not too challenging for you. So what we get here then is, so I'm going to get 2 cos 4x. So 2 cos 4x, which I then times by, that's going to be minus 4. So minus 4 sine 4x. Okay, let's extend that a little bit. So let's just simplify here. What do we get then? So that is minus a sine 4x cos 4x for the numerator. Minus a sine 4x cos 4x. Like so. And that is all over then cos squared 4x. Like that. Can we simplify this here? Well, of course, right? I've got a cos 4x here in the numerator. I've got cos squared 4x here in the denominator, right? So that power reduces by 1. That cancels. And what we get left with here is minus a sine 4x. And that is all over then cos 4x. Well, sine 4x over cos 4x, that is tan 4x. So what I've got here is minus a tan 4x. Okay. And there we go then. So that gives the solution there to a part 1. Now for a part 2 again, sticking with differentiation here. We now want to differentiate this here. So again, pretty straightforward, right? So it's d by dx then of, so we've got 2x squared minus 5 to the power of 6. Okay. So again, clearly we do need to use the chain rule here. So what do we get here then? So the 6 comes down in front, so I get 6. I then times that by the derivative here of the inside of the bracket, so that is 4x, so 6 times 4x there. Like so. And then we reduce the power here by 1, right? So 2x squared minus 5 to the power of 5, like so. So 6 times 4x, that is 24x. We get 24x times then 2x squared minus 5 to the power of 5. Perfect. And there we go then. So that gives the solution to a part 2. That's the next 2 marks there in the bag. So for the final part then of this question here, we do have a little bit of integration, right? So it says, hence show that this integral here is equal to q, where q is an integer to be determined. As it says here at the bottom right, solutions relying on calculator technology will be awarded no marks, right? So we need to show then how we've done this. Now, just notice here then, the integrand here, the thing that we're looking to integrate. So this here, thing that we're looking to integrate, is very, very similar to what we just obtained here in a part 2, right? The difference here is we've got 24x times 2x squared minus 5 to the 5. They've just got x times 2x squared minus 5 to the 5. So this result here is 24 times too many, basically, okay? But we can use this result here to, easily evaluate this integral here. It's actually just an application then of the reverse chain rule, right? If you didn't notice it already. If you did, then brilliant. But like I said, if you didn't notice it, then yes, this is just a reverse chain rule. So let's just put all of this together here then. So this is for part B. We don't have tons of room. So what I will do here is I'll kind of start over on the left-hand side. I can't speak anymore. We'll start on the left-hand side and hopefully we should have just about enough room, but it might be a little bit tight. But let's just see. So the integral here from 0 to root 3. And my pen works. So from 0 to root 3 of this here. So x times then 2x squared minus 5 to the 5. Integrating here with respect to x is equal to then, so as we just said, this here is very close. It's just 24 times too many. So what I can do here is times through then by, or I can write this here as the integral then from 0 to root 3. Let's write over that. Why not? So what have we got here then? So it's going to be 1 over 24 times then d by dx of this here. So d by dx of this here. So that is 2x squared minus 5 to the 6. Okay. Notice here then, put the dx at the end as well. Notice here then, if you're integrating a derivative at the inverse of each of us, they just cancel. So what we get left with here then is 1 over 24 on the outside. So 1 over 24. Now we apply the limits here. So inside here we get 2x squared minus 5 to the 6. So 2x squared minus 5. Oops, that should be to the 6 there. Apologies, let me just quickly redo that so it looks a little bit neater. Oops, there we go. So to the 6 there. Now apply the limits here. So we're going from 0 to root 3. Okay. So in terms of actually evaluating the limits here, pretty straightforward. Start with the upper limit, subtract the lower limit here. So what do we get then? So we get 1 over 24 on the outside. So starting with the upper limit here, I get 2 lots of root 3 squared. So root 3 squared is 3. Times that by 2, I get 6. Minus 5, I get 1. So I get 1 to the 6 there. So 1 to the 6 there. Now for the lower limit here, we subtract that, right? So minus then, I'll put this in a bracket here just to avoid any confusion with the signs. So 2 lots of 0 squared, that's just 0. However, we've got the minus 5 here, so that's minus 5 to the 6. So minus 5 to the 6 there, okay? Like that. Well, minus 5 to the 6, that would be positive, so that's minus a positive number. So the result will clearly be negative. What we get here then is 1 over 24. So 1 over 24 times 1 minus then, I get 15,625. Clearly just use your calculator, right? You don't have to do this off the top of your head. And then again, just roll this into your calculator here one more time. If you do this correctly here, what you should get then, and don't forget the result should be an integer. If you don't get an integer, you know you've done something wrong. But what we do get here is minus 651. Okay. And there we go. So you can clearly see a little bit of a step up in difficulty here. Nothing too crazy, but certainly a little bit more challenging than the previous 2 questions. Okay. Well, there we go then. That gives us the solution here to question 3. Now moving on to the next question here, question 4. As we can see, then we're given the functions f and g here. They're defined as the following, where k is just a non-zero constant. So I've got part A and part B to this question, but part A does involve a few different parts as well. So let's just begin with part A then and work through the first few parts here. Okay, so for A part 1 then, what do we want to do here? So it just says then, find in terms of k, fg of 2. So we've got this composition of functions here, right? Now because it's fg of a value here, it's really quite straightforward. Just start with g of 2, and then whatever g of 2 is, that goes into the function f. Nice and easy, right? So for fg of 2 then, we start with g of 2. We start with g of 2 here. So what is g of 2? So just substitute 2 into the function g here. So I get 1 plus 4 lots of 2. So that is 1 plus 8, which is 9. Minus 2 squared, so minus 4. 9 minus 4, and we get 5. So g of 2 then is equal to 5. What we now find here then is f of 5. So f of 5 here. So obviously this will be in terms of k here. So what do we get then? I'm going to get 5k, that's k times 5. And that's all over 3 times 5, which is 15, plus 2, giving us 17 there for the denominator. So we get then 5k all over 17, just like that, right? And there we go then. So that is fg of 2 there. Just quickly note that here. So fg of 2 is equal to, it's going to be 5k all over 17. Bosh. Nice and easy, right? So that's A part 1 complete. So for A part 2 then, it just says find in terms of k the range of f of x, right? So range of f of x. How do we do this here? Well, I'm hoping it's kind of obvious then that straight away, the range here will be y belongs to a set of real numbers, but we do have a problem in that there is a horizontal asymptote to consider here, right? If you've got a fraction such as this one here, there will always be a horizontal asymptote. So what we need to kind of deduce here basically is what is the equation of the horizontal asymptote, right? Because that would give us the one value here that we cannot take for the range here for f of x, right? So for the horizontal asymptote here then, we look at the actual function here, so kx over 3x plus 2. So what I can do here then is just divide top and bottom by x. So if I do that then, what I get here is k, and that's all over then. So the 3x here, that just becomes 3, and the 2 then becomes 2 over x. Okay, just like that. Now we consider then what happens here as x gets larger and larger, right? In other words, as x tends to infinity. So make a note, where can I do it? That's not confusing. Do it here. As x tends to infinity, then what happens here is the 2 over x, that just tends to 0. That's 2 over an arbitrarily large number. This just basically becomes 0. So I get k over 3, right? So the horizontal asymptote here is y is equal to k over 3. So make a note here. Horizontal asymptote. Horizontal asymptote here is y is equal to k over 3, as we essentially deduced over here. So in that case then, so therefore the range here is, so as we just said then, y belongs to the set of real numbers here. So y belongs to the set of real numbers. However, y cannot be equal to k over 3, right? That is the horizontal asymptote here. So y cannot be equal to k over 3. Good stuff. So that's the solution to A part 2. And then for A part 3 here, what do we want to do then? We now want to find, in terms of k, the inverse of f of x, right? So what can we do here? Well, what I'll do then, I'll just start by replacing f of x here with y, right? So y is equal to kx. So it's kx here, all over 3x plus 2. What we now want to do here is just make x a subject, right? So I'm going to times both sides by 3x plus 2 here. So I get y times then 3x plus 2. So y times 3x plus 2 there. like so. And that is equal to kx. Okay? As we just said then, what we want to do here is make x the subject. So I will need to expand this single bracket here on the left-hand side, get the x on one side, and then we can factor out, right? And we're pretty much there at that point. So we get 3xy here, 3xy plus 2y is equal to kx. Okay? Now, there's two ways to do this, right? I can take the 3xy to that side, or we could take the kx to this side here, and obviously get the 2y and then onto this side here. Either way is fine. Usually there's a slightly neater way to do it. So the neater way here, in my opinion anyway, is to take the 3xy to this side. So I get kx here minus then 3xy, like so, is equal to 2y. Okay? And as we said before then, the aim here is to make x a subject. So to now do that here, we factor an x out from the left-hand side. We get x bracket k minus 3y is equal to 2y. And therefore then, if we want x here on its own, then x here is equal to 2y all over. It's 2y all over k minus 3y. Okay? Now, that isn't the solution here, just be careful, right? What we want then is the inverse of f of x here. So I do need to give it in terms of the inverse of f of x. This is just x is equal to 2y over k minus 3y. It's in terms of y here at this point, right? So in that case, then just replace x here with the inverse of f of x. That's the f with the little minus 1, right? Should be very straightforward at this point here. In your A-level maths career, that's what you want to call it. But anyway, I'm just waffling. Replace the y's with x here. We get 2x all over k minus 3x. There we go. So that is the inverse there of f of x in terms of k. Okay, that's A part 3 complete. And now to finish with them, we have part B, right? So for part B then, we're given this equation here, the inverse of f at 3 is equal to 12 over 5g of 1. Right, so where do I begin here? So let's just start with g of 1 then, because g of x here is just in terms of x. There's no k's to deal with there, so that's fine, right? So g of 1 then, g of 1 here, that is 1 plus 4 lots of 1, so that's 5. Minus then 1 squared, so that's going to be 4. So g of 1 is 4, okay? So what I've got here then is 12 all over 5 times 4, so that's 12 over 20. So 12 over 5 g of 1, that is 12 over 20, which is the same then as 6 over 10, which is 3 over 5, okay? You don't have to simplify it, but it just makes life a little bit easier, right? So what we know here then is the inverse of f of x when x equals 3 is equal to 3 over 5, okay? So this here is the inverse of f of x. Let's just substitute 3 into that. So the inverse of f of x when x equals 3, that is 2 times 3, so that's 6. So I get 6 there. That's all over then k minus 3 lots of 3. That's k minus 9. So this here is equal to 3 over 5. So let's just equate those. So 6 all over k minus 9 is equal to 3/5. Let's just cross multiply here then. So 6 times 5 is 30. Apologies, I'm running out of room a little bit here. We should just about make it. So 6 times 5 is 30. And then 3 lots of k minus 9. Like so. Rather than kind of going through the process of expanding here, let's just divide both sides by 3. So I get 10 is equal to k minus 9. And then clearly, if we just want k here, we just add 9 to both sides, right? So therefore here, k is equal to, I was going to put 9. It's not 9, it's 19. 10 plus 9. There we go. 19. Basic maths is very challenging, but there we go, right? So k is equal to 19. So as you can see then, nothing particularly too challenging there for question 4, I don't think. Obviously, if you do struggle with the inverse here, then you will struggle with the final part of the question because you do need the correct inverse function there. So then go on to find exact value of k, but there we go, right? So that gives us the solution there to question 4. Now for question 5 here, as we can see on the screen then, we have a question on vectors. So what we're told here is the variable points a and b are relative to a fixed origin O, where t is just simply a scalar variable. So a is given us 2t, t, and 3, and b is given us t, 4, and 7. So for the first part of this question here then, part A, we just want to show then that the magnitude of the vector AB can be given as the following. So clearly the first thing that we need here then is just the vector AB. Without that, we clearly can't find the magnitude, right? So let's just find then the vector AB here. So nice and straightforward then. That's just simply the position vector for B minus the position vector for A. And these are relative to a fixed origin O. So it's just going to simply be as column vectors then. So it's going to be T forward 7. So T forward 7 minus here 2t, t, and 3, right? So 2t, t, and 3. Okay, nice and straightforward then. What do we get here? So t minus 2t is minus t. 4 minus t is just simply that, right? I can't do anything else with it. So 4 minus t, and then 7 minus 3 is 4. Perfect. Okay, so we get this here, and this is the vector AB. But what we want here is the magnitude of that, right? So nice and straightforward then. So don't forget here, the magnitude of the vector AB is just simply an application of Pythagoras in 3D space, right? So what we get here is the square root of minus t squared plus then 4 minus t squared. So 4 minus t squared plus 4 squared, plenty of room. Just like that. Let's just simplify here. What do we get? So I've got minus t squared, so that's just simply t squared. You can write this as a product of brackets here, or just do this off the top of your head. Clearly, just be careful if you're going to do that. I'm going to be lazy. I'm going to just kind of do this off the top of my head here. So let's just be careful, right? So 4 times 4 is 16. So I get plus 16. I get 4 times minus t, so that's minus 4t. And we repeat that again in the middle. So minus 4t minus another 4t is minus 8t. And then minus t times minus t is plus t squared. And then finally here, don't forget the 4 squared, giving us plus 16. Okay? And if we just simplify this here then, what do we get? This is for the magnitude of AB here. What do we get then? So we've got t squared plus another t squared, so that's 2t squared there. Good stuff. I've got minus 8t. So there's no more t terms, so it's just simply minus 8t. And then 16 plus 16, giving us 32. Good stuff. So we get this here, which is exactly what we wanted, right? So as required there, bosh, happy days, good stuff, whatever you want to say, QED, whatever floats your boat, but we got the solution. So as required, I'll give it a smiley face as well, right? So there we go. And that gives us the solution to part A. So that's the first 3 marks there in the bag. And now for the final part then of this question here, part B, it just says, hence find the shortest distance between A and B as t varies, right? So let's just do part B then over here on the left-hand side. Now, there's a couple of different ways that you can do this here. You could just differentiate and use calculus. That's absolutely fine. But in my opinion here, the much easier way to do this is to just complete the square on this quadratic expression here, right? And then from there, we can find the shortest distance between A and B as t varies. So as we said then, let's just complete the square here. We do have a slight problem in that the coefficient of t squared here isn't 1. So to deal with that, let's just pull out the 2 as a factor. So that's right here. So the magnitude of the vector AB, pulling the 2 out then as a factor here, we simply get the square root of, so it's 2 bracket t squared minus 4t plus 16. Like so. So now the coefficient of t squared is 1, so we can now complete the square at this point here. So what do we get then? So I've got the square root here of, we'll put the 2 on the outside again. Inside here, I'm going to get t minus 2 all squared. T minus 2 all squared. I'm going to get minus 4 plus 16. So minus 4 plus 16 is plus 12. Like that, right? And now let's just multiply through by the 2 then. So what I get here is 2 bracket t minus 2 all squared. And then 12 times 2 is 24, right? Just like that. Okay. Now at this point here, we're pretty much done then, right? But you do need to kind of recognize here is that the shortest distance, in other words, the minimum value here of the modulus of AB. So let's just make a note here. So I said the modulus, the magnitude, you know what I mean? Same thing. So the minimum here of the magnitude then of the vector AB here, that occurs when this part here is 0 because this is squared, right? So it's always going to be a positive value except for when it's 0. Okay, so it'll always add something to the 24. So the way to minimize this here is to get this part equal to 0. So when does that happen? Well, that's just when t is 2, right? So 2 minus 2 is 0. 0 squared is 0. Times by 2. And this whole part here is just 0. Okay. So the minimum here for the magnitude of the vector AB, this occurs when t is equal to 2. Okay. So what that gives us here then is the magnitude of the vector AB, the minimum of that is equal to, so that would just simply be root 24, right? I just get left with the 24 at the very end. So root 24. And what I can do here then is just simplify this here. So we can write this here then as 2 root 6, right? So 2 root 6. There we go. 2 root 6 there. You could just leave it as root 24. It doesn't ask for it in a simplified form. So root 24 would be fine. You could also give it a decimal if you really want to. It doesn't say keep it in exact form. So root 24, 2 root 6, or a decimal equivalent there is absolutely fine. Okay. And there we go then. So that gives us the solution to part B and the solution to question 5. Now for question 6, then we have the first of the modeling type questions for this paper here, right? As we can also see on the screen here, this is modeling with parametric equations, everybody's favorite topic. So for question 6, then what we're told here is modeling software for the shape of the path of a water slide is given by the following parametric equations. So just in case they are a little bit small to read on the screen here, x is equal to 3 plus ln t, and y is equal to 4 sine 3t for t between 0 and pi over 3. We've also got this figure 1 here, which just kind of shows the, the path here of the water slide as a graph, just kind of help visualize the problem. So for the first part of this question here, then part A, let's just do this at the very top here. It just says then, find the coordinates of the point where t is equal to pi over 9. Nice and straightforward then. All we simply do here is just substitute t equals pi over 9 into this parametric equation here, and also this parametric equation here. As we said then, right? Nice and easy. So let's just make a quick note here. When t is equal to pi over 9, what do we get here? So in that case then, x here is equal to, so it's 3 plus ln of pi over 9. So 3 plus ln of pi over 9. So just throw this here into your calculator. And if I run this to say 3 significant figures here, what I get then is 1.95 there. Okay, so that's the x coordinate there. We also need the y coordinate. So y here is equal to 4 sine of 3t. So that's 4 sine. And then that's 3 lots of pi over 9. So 3 pi over 9 is just the same as pi over 3, right? So 4 sine pi over 3. Again, just throw this into your calculator here. In exact form, this is 2 root 3. But again, I'll give this as a decimal then. And again, to 3 SF here, this is 3.46 there. Okay. And in that case, then the coordinates here are 1.95 and 3.46 there. Perfect. Okay. So I guess the first 2 marks in the bag there and the solution to part A. Now for the next part then, part B here, let's just continue underneath. We're told this bit here, right? So given that 1 unit on the model represents 4 meters in real life, for part B then, what we want to do here is just find the maximum height of the water slide. Now, it is just 1 mark, so I'm not really expecting too much work here. What does sometimes happen is students see the word maximum height and instantly think of differentiation, which isn't a bad thing, and I kind of like that train of thought. But for this question here, for just 1 mark, we're definitely not expected to do parametric differentiation here, anything like that. To find the maximum height here, we just consider then this parametric equation here, so 4 sine 3t. So the maximum value of y here, that occurs when sine of 3t is equal to 1, right? So max value of y, that occurs when sine of 3t is equal to 1. Okay, so this part here is equal to 1. That's the maximum value. So what that tells me here then is the maximum value of y must be 4 times 1. So y max here, so y max then is equal to, so it's 4 times 1, as we just said, right? Which just simply gives us 4. No prizes for guessing that. But be careful here. This isn't the maximum height of the water slide, because what we're told here is 1 unit on the model represents 4 meters in real life. So what I've got here is 4 units on the model. So if 1 unit represents 4 meters, then the maximum height, so therefore max height, that is going to be equal to, so the maximum height here is, it's going to be 4 times 4, right? 4 times 4, giving us 16 there. So don't forget the units as well, right? This would be meters here. So 1 unit is equal to 4 meters. So that is 16 meters there. Okay. And again, that is just 1 mark, so we're not really expecting too much work there. But there we go. So that's the solution to part B. Now for part C then, this is where we do require a little bit more room to actually answer the part of question, or that part of the question. English is hard. So what I will quickly do here is just pause the video, clear the screen, then we can continue with part C and part D to finish with. So as we can see then, right, we've cleared the screen here at this point. We've completed part A and part B. There's still part C and part D to go here. So let's just start part C then at the very top here. So for part C then, it just says find the horizontal distance covered during the descent of the water slide. Now this is 4 marks, so we are probably expecting a little bit more work here. So let's just see what we're dealing with then. Now, as you can kind of see from figure 1 here, the descent starts when the slide reaches its maximum height. So that would be this point here, right? This is the maximum height. And from here on out, that is the descent, right? So that occurs then at the maximum height, as we just mentioned. And as we discussed in part B, the maximum height occurs when sine 3t is equal to 1. Now, why is that important? Well, from here, we can now find the value of t at the maximum height. Okay, take arc sine of both sides here. We get 3t is equal to arc sine of 1, which is just simply pi over 2, yes, pi over 2, just like that. And if we just want t here, what we simply do then is just divide both sides by 3, right? So t here is equal to pi over 6. Good stuff. So we now know here that the start of the descent here is when t is equal to pi over 6. But we also need here is the value of t at the end of the descent, which, as you can kind of see here from figure 1 again, that is when t is equal to pi over 3, right? That's this point here. That's the end of the descent. So the descent ends, I can't speak anymore. I've said the word descent too many times. So the descent, there we go, the tongue twister, that ends when t is equal to pi over 3, okay? So this is the start. And it ends then when t is equal to pi over 3, okay? Just put n there, just kind of highlight that, okay? So what I now need here is the x values for these 2 values of t here. Why is that the case? Well, what we want here is the horizontal distance, right? So for the start of descent then, make a quick note here. So start of descent. What we simply do here then is just substitute t equals pi over 6 into x here. So that's 3 plus then ln of pi over 6. I won't give these as a decimal here. I'm going to keep these in exact form. You'll see why in just a moment. And then for the end of the descent here, so end of descent, what is that? So that's going to be when t is equal to pi over 3, right? So 3 plus ln pi over 3. So 3 plus ln pi over 3. So the horizontal distance here is the end of the descent minus then the start of the descent, right? So make a quick note here. Horizontal distance. Horizontal distance is given as then, as we just said here, it's the end of the descent. So that's 3 plus then ln of pi over 3 minus then the start of the descent, right? So that's 3 plus ln of pi over 6, just like that, okay? What I can see straight away here is that 3 cancels with that 3, 3 minus 3. I've got ln of pi over 3 minus ln of pi over 6. So ln of pi over 3 minus ln pi over 6. What we can do here then is write this as a single log. That is ln of, so it's pi over 3 all over pi over 6, just like that. And what does that give us here then? Well, this is just simply ln 2. Okay, so be very, very careful here. The horizontal distance covered isn't ln 2, essentially, because this is just 1 unit here. As we're told at the beginning then, 1 unit on the model represents 4 meters in real life. So just be very, very careful for that here. So in that case, then the horizontal distance is, so therefore horizontal distance is so it's ln 2 multiplied by 4, right? It's 4 ln 2 meters, which is just essentially, what is that? Throw that into your calculator, and again to 3SF here, I get 2.77 meters there, okay? And there we go. So that gives us the solution to part C. As we said, 4 marks for that. As you can kind of tell, there's a little bit more work involved, but nothing too crazy. And then for part D here, just a 1 marker. It just says then, hence find the average gradient of the descent. Right, so for the average gradient here, again, if you see that word gradient, you might be thinking of differentiation, but again, it's just 1 mark. We're clearly not going to be doing parametric differentiation here. But what we are going to do then is just consider the gradient here over these 2 points, right? That is the average gradient here. So don't forget then, for the gradient here, a throwback to GCSE maths when times were easier. It's going to be y2 minus y1 all over x2 minus x1, okay? So for y2 here, that's going to be 0 at this point here, right? I also don't have tons of room, so 0 minus then y1, that is the maximum height here. So our maximum height here, I've got rid of it, but it was 16. So apologies, I probably should have kept that on the screen here. We should have it from the previous part of the question, right? So the maximum height of the water slide, that was 16, so it's 0 minus 16. And that is all over then x2 minus x1. Now, x2 minus x1 is the horizontal distance that we've just found in part C, okay? That's this horizontal distance here, which, as we've just found then, was 4 ln 2. That's 4 ln 2. So this gives me then minus 16 over 4 ln 2. That just cancels down then to give me minus 4 over ln 2. So minus 4 over ln 2. I don't have much room, so to finish with then, part D here. Put it up here. Minus 4 over ln 2. If we give this as a decimal, as we've kind of done for the rest of the question, right? What I get here then is minus 5.77 there for the average gradient, actually. So it's not just the gradient, is the average gradient, okay? So this here is the average gradient, okay? And there we go. So this here was the solution to part C, and then just the final one marker. I can't speak anymore. Just the final one marker here for part D, right? Giving us the average gradient, okay? And there we go. So that gives us the solution there to question 6. Now for question 7 here, we have the following. It looks a little bit spooky, right? I've got this summation here from n equals 1 to infinity of this here. Looks a little bit grim. But it's actually not too bad, right? First off, it's only 3 marks, so I know the number of marks doesn't dictate how easy it should be, but for 3 marks here, we're not really expecting too much work, especially given that it is just question 7, so kind of around the middle of the paper here. I'm not saying it's the most straightforward question in the world, but, you know, it's not like question 14, question 15, where, you know, we do consider it to be a little bit more challenging, okay? So if you get a question such as this one here, there are 2 things that I would mention first off, right? As soon as I see a summation here from n equals 1 to infinity, I am thinking straight away here about a geometric series and the sum to infinity, because 99 times out of 100, that is what the question is kind of linking to. And then the second thing here is, if you're really not too sure where to kind of begin, just start with the first few terms of this series here, right? This at its very core is just a series, okay? So just start with the first few terms of the series, just see what's happening, and from there, sometimes it kind of illuminates what you need to do then for the next step of the question, okay? So let's just start then, as we just said here, with the first few terms. So we'll start with u1 here, the first term in the series. So that is when n equals 1 here. So what do we get then? So we get 1 over 2 to the 1. That's a half to the power of 1. And then times it by sine of 90 times 1. So sine of 90 degrees there. 2 times it by sine of 90 degrees. Well, let's just evaluate this here then. 1 over 2 to the 1 is just 1 over 2. Sine of 90 degrees is just 1, right? So it's a half times 1, which just gives us 1 over 2. Right, that's all fine. What about u2 then? So that would be the second term in the series here. So that's going to be 1 over 2 to the 2. We then times it by sine of, it's going to be 180 degrees here, right? 90 times 2 is 180. So as we just said then, sine of 180 degrees. Again, just throw all of this here into your calculator. That's 1 over 4. Sine of 180 degrees is 0. So 1 over 4 times 0 is just 0. Okay. Let's just keep going here. u3 then. That's going to be 1 over 2 to the power of 3 times then. So it'll be sine of 270 degrees. So sine of 270 degrees. What is that then? So that's going to be 1 over 8 there. I get 1 over 8. And then sine of 270 degrees, that is minus 1, right? We times that by minus 1, giving us then minus 1 over 8. Right, okay. Some of you at this point here might spot what's going on. For some of you, you might need an extra term or 2. That's absolutely fine, right? So I'll kind of drag it out, and I will do the next 2 terms here just to really illustrate what is going on. But if you can spot at this point here what you need to do, right, then just go from there. That's absolutely fine. So u4 here, that would be the 4th term in this series. That's going to be 1 over 2 to the 4, and then times it by sine of 360 degrees. So this is 1 over 16, right? But sine of 360 degrees is just 0. So 1 over 16 times 0 is just 0. Okay? Now, if I just do one more term here then to finish with, I'm hoping it is very clear at that point, right? I'm not doing any more terms after that. So if you haven't got it by that point, then unlucky. So u5 here. So that's going to be then 1 over 2 to the 5. I times that by sine of 450 degrees. Yes. Sine of 450 degrees. I mean, feel free to just use your calculator. You don't need to do this off the top of your head. That is 1 over 32. 1 over 32. Sine of 450 degrees is 1. I've got 1 over 32 times 1, which is 1 over 32. Right. So I've got the first 5 terms here. Now, hopefully, like I said then, it is clear what we're doing at this point here. But if not, just consider then what I mentioned at the beginning of the question here, right? As soon as I see a summation like this here, or a series that goes from n equals 1 to infinity, such as this one here, I am thinking straight away then the sum to infinity here of a geometric series, okay? Now you might be thinking then, well, hang on, how does that work? Because U2 and U4 here, they're both 0, right? That's true. And the same would apply here to U6, U8, U10, so on and so on. So basically, for this series here, all of the even terms then, they'll just be 0, right? But if we kind of just ignore those, so ignore the even terms here and just consider then the series here that is formed by the odd terms, so U1, U3, U5, U7, U9, so on and so on, then what happens here is the non-zero terms form a geometric series, right? So let's just mention here, non-zero terms. So the non-zero terms here form a geometric series. So they form a geometric series here. Now, if we're going to consider then a geometric series here, we need two things. We need the first term, which, as we can see here, is just 1 over 2. So what we'll say here is A is 1 over 2. And then what about R here, right? The common ratio. So R here, that is the common ratio. Well, again, hopefully it's obvious that R here is just minus 1 over 4. But if you're not sure, then just take U3 here and divide that by U1. And you can verify that then with U5 divided by U3. Either way, what you should get here is minus 1 over 4, right? Just like that. So what we can find here then is the sum to infinity, right? So therefore then, the sum to infinity here, well, the formula then is A all over 1 minus R. So A here, that is 1 over 2, right? I've got a half there. And that is all over 1 minus R. So 1 minus here, minus 1 over 4. So for the denominator here, that is 1 plus 1 over 4. So that's going to be 4 over 4. Plus 1 over 4, so that's 5 over 4. So I've got 1 over 2, all over 5 over 4. Simplify this here then. And what we get here is we get 2 over 5, exactly as we required, right? So as required there. Perfect. Happy days. We always like getting the correct solution. Give it a smiley face as well. I often get asked as well, do you need to put as required? No, you don't. I just like to do it. That's just a preference thing that I've kind of developed over the years. It just kind of shows that we've got the correct result there and question is done right. No more work is required. So there we go then. 3 marks in the bag there. And that gives us the solution to question 7. So moving on to the next question here, question 8, we do have a very standard type of question, right, on differentiation from first principles. What we want to do here, as we can see on the screen, right, is prove from first principles that the derivative of cos theta with respect to theta is just simply minus sine theta. And we're given 2 extra bits of information here we can use then. We've outproved the formula for cos of a plus or minus b. And we can also assume here that as h tends to 0, sine h over h tends to 1, and cos h minus 1 over h tends to 0. Now, you've probably seen these types of questions here before, I'm hoping anyway. Like I said, it is a very kind of like standard differentiation from first principles question. Now, these do come up every so often. It's been a couple of years, I think, at the very least since this last came up. And I'm kind of just taking a bit of a guess here that it might come up again this year. Whether I'm right, we kind of, we wait to see. But there's no harm in kind of working through this as a question, right? You should always be able to prove the derivative of sine theta and cos theta from first principles, right? Especially as A-level math students. So where do we begin here? Well, for any kind of like differentiation from first principles question, what I always like to start with then is f of x, or in this case here, f of theta. I'm going to start with f of theta and also f of theta plus h. Okay, I like to start with both of these here. So f of theta then, that's the thing that we want to differentiate, which in this case here is just simply cos theta. So f of theta is cos theta, and then f of theta plus h, that's going to be cos of theta plus h. Okay, now what we also need here is the formula then for differentiation from first principles. So that result then, so the result here for differentiation from first principles, that is the limit as h tends to 0. in this case here, given that we're working with theta, I will give the formula in terms of theta, but in the formula book it is given in terms of x, but it doesn't really matter, right? So what we've got here then is f of theta plus h minus f of theta, and that is all over h. So this here then is the formula that we're going to use, right? Let me put kind of like a bubble around this here, just to kind of really highlight the importance of this result. But again, it is given in your formula book. It's not something that you do need to kind of like memorize. So don't worry about that. So let's just apply then f of theta and f of theta plus h to this formula here. So I'll do that at the very top here. So in that case then, d by d theta here of cos theta, that is equal to then this formula here. So that is the limit. It's the limit here as h tends to 0 of f of theta plus h. That's cos of theta plus h. Cos of theta plus h minus then f of theta, which is just simply cos theta. So minus cos theta. And that then is all over h. Right, we're off to a good start here. So where do we go from here? So what we're told then is we can use, without proof here, the formula for cos of a plus or minus b. So again, just go back to your formula book here, right? You do not need to memorize the double angle formulae. If you can, it's a weird flex, but all good. Use it as you can, but I can't memorize it. So I refer to my formula book here. So the formula then gives us the following here. So we do need a little bit more room now because it gets a little bit messy, but let's just continue then. So what we've got here is the limit as h tends to 0 of, so it's quite a long expression here. So cos of theta plus h then, what does that give us? So I get cos theta cos h. So cos theta cos h. And then what we do here is we minus sine theta sine h. So minus sine theta sine h. Okay. Do not forget the minus cos theta here as well. It's very easy to kind of forget that in and amongst all of the working. So minus cos theta, and all of this here is all over h. Okay, perfect. So at this point here, we kind of got off to a good start. We kind of laid the foundations. And from this point here, then it's just kind of like a matter of simplifying, getting it into the correct form then so that we can utilize this limit here and this limit here. Okay. So what I will do here then is put the minus cos theta with the cos theta cos h, right? Because at some point here, we need to get it into these forms here, right? So I'll do this underneath then. What we get here is the limit as h tends to 0 of then. So I get cos theta cos h minus cos theta. So cos theta cos h minus cos theta minus then sine theta sine h. So minus sine theta sine h. Okay, and again, all of this here is all over h. And yes, if you're going to ask then, you should really be writing the limit as h tends to 0 at each and every step here. It's a good habit to get into, especially if you're going to want to do maths at university. It's an important thing to be doing. So don't be lazy, just write it down each and every time. So we've grouped them together here. What I will do then is factor out the cos theta here. So if I do that then, what I get here, and I'll do it over on the left-hand side just so we've got a little bit more room, because these questions do always take quite a bit of room then. So I've now got the limit here as h tends to 0 of them. So as we just said, right, let's just factor out the cos theta here. I get cos theta bracket. So then get cos h minus 1. So cos h minus 1, like so. What I'll also do here as well, I can't speak anymore, but what I will also do here is write these now as two separate fractions. So to do that, what I will do here is put a bracket around the full limit. We're taking the limit of the full expression, right? So it's cos theta times cos h minus 1, just factor out the cos theta. This is all over h, like so. And then what we do here is we subtract sine theta sine h over h, right? So minus then sine theta sine h, and that is all over h, just like that, okay? So we get this here. Now, if we're taking the limit of a difference or a sum like this here, what we can actually do then is take the limit of the individual fractions, right? We apply something called linearity. So I can take the limit of this fraction here minus then the limit of this fraction here. So let's just do that underneath then. I've got the limit as h tends to 0 of this fraction here. So that is cos theta bracket cos h minus 1. That is all over h, like so. And then we subtract here the limit, again, as h tends to 0. And I do appreciate it is quite tedious doing this each and every time. But again, it is important to show this. Of then sine theta sine h. So sine theta sine h all over h. Right. Looking good. Now, what we can also do here is take then the cos theta and the sine theta outside the limits, right? Now, cos theta and sine theta, they are just simply constants. And with limits, we can apply again linearity here and take the cos theta and the sine theta outside the limits, okay? So if I do that then, what I get here is, I'm going to get cos theta times the limit then as h tends to 0 of cos h minus 1 over h. So let me try that down here. So as we just said, then I get cos theta times the limit as h tends to 0. Apologies, by the way, my handwriting is terrible, but hopefully you can just about follow along. Of them, so as we just said, I get cos h minus 1 over h. So cos h minus 1 over h there, like so. Minus them, again, just taking the sine theta outside the limit here. I get minus sine theta. So minus sine theta times the limit here. Again, as h tends to 0 of sine h. So sine h over h there, okay? And this is perfect because what we've now got here are these two expressions, right? I've got cos h minus 1 over h. That tends to 0 when h tends to 0. And we've also got here sine h over h, which tends to 1, again, as h tends to 0. Perfect. So if we now consider the limits then, make a quick note here. So now consider the limits, which we're given anyway, so we don't really need to consider it as such. They're just given anyway, but we kind of describe it as considering the limits. So now consider the limits. And what I get here, let's just do this a little bit further up then, is I get cos theta times this here. So essentially, as h tends to 0, this here tends to 0. It just basically becomes 0, right? So that becomes cos theta. So that's cos theta times 0 minus them sine theta times this limit here. Well, this limit here, as h tends to 0, this becomes 1, right? So that's minus sine theta times 1. So minus then in a bracket here, sine theta times 1. Well, that's just 0. This here then becomes minus sine theta. So therefore then, what we can now see here is the derivative with respect to theta of cos theta. That is equal to minus sine theta here, as we've just shown then from first principles, right? It's always beautiful to work through. And, you know, it is quite a tedious question in a way. I can see this just took under 11 minutes just to answer this question here. And it is only worth 5 marks, but, you know, for 5 marks, it's really not too challenging, I don't think. Just quite a tedious process, okay? But there we go then. So that gives the solution there to question 8. Happy days, right? As we've got there. Perfect. Now for question 9 here, as we can see on the screen, then we do have this tasty looking integration question. So what we can see straight away here is it's integration by substitution, right? It doesn't take a genius to figure that out. It just says in use of substitution, u is equal to the square root here of x cubed plus 4 to show that this integral here is equal to the following. It looks a little bit grim, where k and a are constants to be found and c is an arbitrary constant. So when it says that c is an arbitrary constant, it just means the constant of integration. Nothing too fancy, right? And it's just 5 marks for this. So where do we begin here? Well, to begin with then, what I will do here is just start with the substitution, right? So u is equal to the square root then of x cubed plus 4. Now, rather than keeping that in that form, so the square root of x cubed plus 4, let's just give that in index notation, right? Or index form here. So that is just simply then u is equal to then, so it's x cubed plus 4 all to the power then of 1 over 2, right? That is much easier to work with here because what we also need then is something for dx here as well. Okay, whenever you've got kind of like an integration by substitution, such as this one here, you do also need to replace then the thing that we're looking to integrate with respect to, right? So in this case, say dx, sometimes it might be d theta. Like I said, then in this case here, it's just dx, right? So to obtain that, what I need to do here is differentiate u with respect to x. I get du by dx here. So du by dx then, well, to obtain that here, clearly we do need to apply the chain rule, right? So applying the chain rule here, what do we get then? So we get 1 over 2 in front of this expression here. And then we also times that by the derivative of the inside of the bracket. So if you differentiate the inside of the bracket here, we get 3x squared. So that's 1 over 2 times 3x squared. So I get 3x squared over 2 outside the bracket. So 3x squared over 2 outside the bracket here. We then get this bracket here again, but we need to reduce the power by 1, right? So I get x cubed plus 4, and that's the power then of minus 1 over 2. Perfect. Now, a much easier way to work with this here then is to rewrite this as, it's going to be 3x squared. I get 3x squared here, and that is all over them. So this is x cubed plus 4 to the power then of minus 1 over 2. So that is the same then as 1 over the square root here of x cubed plus 4, right? We also times that by 2 as well. So what I get here then is 2 lots then of x cubed plus 4. And that's the power then of 1 over 2. Again, you can write that as a surd or a square root here, but just keep life easier. We'll just keep that in index form or index notation, okay? Now this is du by dx. What we want here is just dx. So to begin with then, let's just flip this here to give us dx over du. So dx over du. So that is just simply, again, just take the reciprocal of this, right? So we get 2 bracket x cubed plus 4. That's the power then of 1 over 2. And that is all over 3x squared. Just like so. And then finally here, we just want dx, right? Just times both sides by du. So therefore dx here is, so it's 2 bracket x cubed plus 4 to the power then of 1 over 2. And this here is over 3x squared. We times it by du to give us following. Right, perfect. So what we can now do here is when we rewrite the integrand here, the thing that we're looking to integrate, we can now just substitute dx in as this here, okay? I appreciate at this point here, it's took us a few minutes already just to get to this point, but with these types of questions here, it is important that you do take your time at the very beginning of the question. Make sure that kind of like the basics and the fundamentals here are all correct, because otherwise, once you start substituting in incorrect things, then it'll start to rapidly fall apart, okay? Because things won't cancel and it won't work, basically. So just take your time, don't rush it, okay? So we get this here. So at this point here, then let's just now rewrite the integrand. So originally what we had then is the integral here of 9x to the 5 over the square root then of x cubed plus 4, integrating here with respect to x, right? Now, the square root then of x cubed plus 4, this part here in the denominator, that's just simply u, because that's what we're given here for the substitution, right? So that's nice and easy. dx, we've obtained the correct expression for that. That is this here. And normally what you would also do here is rewrite the integrand into an expression for u. Now for this one here, I won't do that because it's going to be much easier to just keep this as 9x to the 5, and you'll see why in just a moment. So let's just rewrite this here. So what we get then is, so I've got the integral here then of 9x to the 5, as we just said, we'll keep that as it is. That's 9x to the 5. That is all over them. This here, which is just simply u. And then we have dx. So dx is all of this here. Now just notice here, this is x cubed plus 4 to the power of 1 over 2, which is just simply u. So I've got 2u over 3x squared. Okay. So that is 2u all over 3x squared. Okay. I'm integrating here then with respect to u, so du at the very end. And at this point here, you can hopefully see then why I've kept this as 9x to the 5, okay? Because what's going to happen here then is this will simplify with the 3x squared here, and I've also got a 2u and a u here, so things start to cancel down quite nicely at this point here, okay? As we said then, this u here and this u just cancel. What I've also got here then is 9x to the 5 over 3x squared, so 9 over 3 is 3, and then x to the 5 over x squared is x cubed. So what I've got there then is 3x cubed, but we times it by 2. There's 2 here that's been left over, so I get 6x cubed, right? So now the new integral here is the integral then of, as we just said, right, 6x cubed, yes, like so. And we're integrating here with respect to u. Now you might be thinking, what? How does that work? Given that we've got 6x cubed here, and that's the correct line of thought here, because that's a problem, right? If we're integrating here with respect to u, but we've got the expression here, or the integrand in terms of x, that is a problem. So what we now do here then is we just go back to, or we just go back, I can't speak, we just go back to the original substitution here, right? So u is equal to then the square root of x cubed plus 4. If I've got then 6x cubed here, what I need here is x cubed, right? So if you go back to this here then, square both sides. So u squared is equal to x cubed plus 4. And in that case then, x cubed here is u squared minus 4, right? So I've got 6 lots of this here. This now becomes then the integral here of 6 lots of this here. So 6u squared. To get 6u squared minus 4 times 6 is minus 24. And we're integrating here then with respect to u. Okay? So at this point here, the integration becomes straightforward year 1 integration, right? Add 1 to the power, divide by the new power. So I get 6, I'm going to say x, not 6x, it's 6u. So 6u to the 3 over 3, which gives us 2u cubed. So I get then 2u cubed, like so. I also get here minus 24u. That's just a constant. So once we integrate with respect to a variable, it becomes that constant multiplied by the variable, right? Which in this case here is u. Get minus 24u. And don't forget here as well, right? Our constant of integration. We don't have any limits here on the original integral. So we need our plus c as well. Perfect. Okay. Now, we're getting pretty close to something of this form here. But as we can clearly tell, we're not quite at that point, right? Now, there's 2 ways to kind of really go about this here. You can go straight back into, replacing u cubed here in the u with these expressions that we obtained here at the top. Or what you can also do here is factorize at this point. So I'm going to factorize at this point here. In my opinion, it makes the calculations a little bit easier. You can just go straight into, using the substitution here and then factorizing a little bit later on. But given that it's in terms of x, I think it's a little bit trickier to see. So I'm going to do it here in terms of u, right? So factoring out then a 2u here, I get 2u, bracket then, so that's going to be u squared there. So u squared minus then 12. So 2u times 12 gives me minus 24u. Perfect. Don't forget the plus c again, like so. And now at this point here, I will now use the substitutions, right? So I've got u squared here, it's x cubed plus 4, and u is this here. Okay, so just replace u with this here, and u squared then with x cubed plus 4. Okay, so doing that here then, underneath, what I get is 2 bracket, I get x cubed plus 4. That is the power then of 1 over 2. That is just 2u, right? So that's this here. So that's the power then of 1 over 2. I've then got here inside the bracket u squared minus 12. Well, u squared is x cubed plus 3. So I get then inside the bracket here x cubed plus 4 minus 12, like so, with the plus c again here at the very end. And then to finish with, let's just simplify inside this bracket here. And therefore then, what I can see here is this integral. The original integral here, that is 9x to the 5 all over the square root then of x cubed plus 4. With respect to x here is equal to, we get 2 lots of x cubed plus 4 to the power 1 over 2 So x cubed plus 4 to the 1 over 2 times then, so that's going to be x cubed, and 4 minus 12 is minus 8, right? So I get x cubed, I can't speak anymore. We're nearly there. So x cubed minus 8. Perfect. And plus c as well there at the very end. And there we go. Perfect. So what I can see here then is k is this power. So therefore then, k here is 1 over 2. And a is this number here, which is a, right? So a is 8. And because it's minus 8 here, and they give it as minus a, we do take a as positive 8. And there we go, then we don't need anything else, right? C is just an arbitrary constant. And there we go, I'm pretty much losing my voice at this point here. But there we go then, so that gives us the solution there to question 9. Now for question 10 here, as we can see on the screen, right, we have a very standard trigonometry style question where the first part is based on trig identities. And then the second part here, we're going to solve a trig equation using the previous trig identity in the previous part of the question, if that does make sense. So that's enough of the waffling. Let's just get started then with part A, right? So as I said, very standard here. So what we're given then is that cos 2 theta minus cos theta plus 1 cannot be equal to 0. So we want to show the following here. So sine 2 theta minus sine theta all over cos 2 theta minus cos theta plus 1 is equal to tan theta for the first 3 marks then of this question here. Now, these types of questions here, trig identities, a lot of students don't really enjoy these types of questions. And it kind of goes for everything maths related here and just more generally anything in life. But the more that you practice these types of questions here, I promise you they get a lot easier. The reason why is because you kind of get used to the things to be expecting here. So what I can see straight away here is I've got sine 2 theta and cos 2 theta. So there's a very good chance then that we do need to use the double angle formulae for this trig identity here. And what I can also see then is we have tan theta here on the right hand side. So what I'm expecting then is once we kind of use the double angle formulae here, we should hopefully be able to simplify and cancel. And what I would expect then is we get sine theta over cos theta, right, to give us tan theta there. That's what I'm kind of expecting here. So we'll see if that works out to be the case. Maybe not, but there's a very good chance that is the case. Okay. So let's just start then with the double angle formulae here. We've got sine 2 theta. So sine 2 theta here, that's just simply 2 sine theta cos theta, like so. Now that's promising because straight away, my spidey senses are tingling here. I've got sine 2 theta, which is 2 sine theta cos theta minus sine theta. So that would suggest to me then we can pull out a sine theta as a factor. I'll get left with something else. And then hopefully that will cancel with the something in the denominator as well. And again, I'm hoping that I can factor out a cos theta here in the denominator. So as we just said then, we're hoping to factor out a cos theta in the denominator here. So for cos 2 theta then, we're going to express that here then as 2 cos squared theta minus 1, right? So 2 cos squared theta minus 1. And again, that's promising because we can play a factor of cos theta there. Okay. So let's just do that here. And let's just replace obviously sine 2 theta and cos 2 theta with their respective double angle result. So we've got sine 2 theta, so that's 2 sine theta cos theta. 2 sine theta cos theta minus sine theta. That is all over them. So that's all over cos 2 theta, which is this here. So 2 cos squared theta minus 1 minus cos theta plus 1. Well, straight away then, the minus 1 and the plus 1, they just cancel. So let's apply the relevant factors here. I can play a factor of sine theta within the numerator. We get sine theta bracket. So what do we get here then? We play with sine theta as a factor. We get 2 cos theta minus 1, right? 2 cos theta minus 1, just like that. And doing the same here then with the denominator. As we can see here, right, we can play a factor of cos theta. We get cos theta bracket. So again, this must just be 2 cos theta. So 2 cos theta minus 1. Perfect. Because what's going to happen here is these common factors will cancel just like that. You get left with sine theta all over cos theta, which, as we're aware then, is just simply tan theta. So as we kind of expected then, we got sine theta over cos theta, giving us tan theta. And again, it all comes with practice. So the more of these that you do then, I promise you they get a lot easier. So keep up the practice. But there we go then. That gets to the first 3 marks here for part A. So for the final part then of this question here, part B, let's just continue underneath here. We will need a little bit of room then for part B. So it says, hence solve for x between 0 and pi. This equation here, which is pretty much identical to what we had in part A, right? Giving our answers to 3 decimal places. So we've got this here on the left-hand side, which is identical to this here, with the exception of it being now in terms of theta. In terms of x as opposed to theta, as it was in part A, but that's fine. And then the right-hand side here is equal to 3 cos x. So we know then that the left-hand side here is just simply tan theta, right? Or in this case here, tan x. So what we've got here then is tan x is equal to 3 cos x. Okay, so tan x then, I can write that as sine x over cos x. Okay, I've got sine x here over cos x is equal to 3 cos x. Okay, let's just times both sides then by cos x here. And I'll do that over here, just so I've got a little bit more room then to continue with this question here. So I get sine x. So sine x is equal to 3 cos squared x. We've got sine x is equal to 3 cos squared x. So what I can do here is replace the cos squared x with 1 minus sine squared x, right, and get everything in terms of sine x. And from there, we can hopefully go on to solve the quadratic equation. So as we just said then, replace cos squared x with 1 minus sine squared x. We get 3 lots of 1 minus sine squared x is equal to sine x here. I'm going to get 3 minus 3 sine squared x is equal to sine x. So let's just take everything over to the other side here to ensure that the sine squared term is positive. What we get here then is 3 sine squared x. I've got the plus sine x here in the middle. And then finally, minus 3. And all of this here is equal to 0. Perfect. So at this point here, you can check that this factorizes, but unfortunately in this case here, this does not factorize. So let's just use the quadratic formula here to solve this then. So what do we get here? So sine x then is equal to, so get minus b, so that's minus 1 plus or minus then the square root here of, so it's b squared, so that's 1 squared, minus then 4 times a, which is 3, times c, which is minus 3. Close that bracket, extend that, and this here then is all over 2a, so 2 times 3, giving us 6. So let's just simplify here. What do I get then? I've got minus 1 plus or minus then. So under the third here, that's obviously 1, minus this here, so that's 4 times 3, which is 12. Times it by minus 3, I get minus 36, that's 1. Minus 36, that's 1. Plus 36, giving us root 37 there. Like so. And this here is all over 6. Now, we do need to be slightly careful here. As we're told at the beginning here, x is between 0 and pi. So what we require here then is for sine x to be strictly greater than 0. So in that case, then we omit the negative solution here. So I'll just rub it out. We'll get rid of that there. Okay. So we get this here, right? Now what I want here is just x. This is sine x being equal to this here. So on your calculator then, just do arc sine or sine inverse of this here. And if you do that correctly, then what we get here is x equal to 1.01. Now that is to, I should have done it to 3 decimal places. So in fact, let me change that. I want it to 3 significant figures. So not 3 decimal places, but 3 significant figures. Apologies. I originally changed it and then changed it back, but I mean significant figures here. So I'm going to give this here then for x as 1.01, like so. Now, for the next solution here, because we're between 0 and pi, the next solution here is going to be pi minus this solution here. You can obtain this using a cast diagram, or you can draw a quick graph if you really want to of sine. But either way, this is pretty trivial, right? Let's just do pi minus this here, so 1.01. If you do this correctly, then we should get here for the second solution is 2.13 there, okay? So there we go. There's no more solutions now in this domain here for x between 0 and pi. So we get 1.01 and 2.13 there. Okay, so just the two solutions, really straightforward, right? I'm probably quite a little bit, probably a little bit generous here in terms of the marks, but never mind, right? I'm being generous. But there we go then. So that gives us the solution there to question 10. Now for question 11 here, this question is assessing two different topics within A-level maths. As we can see on the screen here, part A is based on proof by contradiction, everybody's favorite topic, right? And then the final two parts here, so part B and part C, are based on a geometric sequence. So let's just begin then with part A here. So part A is also kind of based on a geometric sequence, but the focus is more on proof by contradiction, okay? So what we're told here then is three consecutive terms in a sequence of real numbers is given by the following. So I've got k, 2 plus 3k, and 5 plus 4k, where k is just simply a constant. So for part A then, what we want to do here is just use proof by contradiction to show that this sequence here is not a geometric sequence. So it's not a geometric sequence. Right, so it's proof by contradiction. We always start with an opening assumption here. So what I'm going to assume here then, so I will assume then that the three terms here that we're given in the sequence of real numbers, I will assume then that these three terms here do form a geometric sequence, okay? So assume three terms. So assume the three terms form a geometric sequence. Okay. Now, if these three terms here form a geometric sequence, then you should be aware here, we take the middle term, divide that by the first term, that should be equal to the third term divided by the second term. So let's just write that underneath them. So 2 plus 3k all over k should be equal to then 5 plus 4k all over the middle term here of 2 plus 3k. Okay. Now, at some point here, we need to arrive at a contradiction, right? So what I can do here is form a quadratic equation, right, by cross multiplying here. And if we need a contradiction here, and we know that the three consecutive terms here in a sequence of real numbers, this being the clue here, real numbers, I am expecting then, if I form the quadratic equation here, it shouldn't have any real solutions. That's what I'm kind of expecting here, right? So let's just cross multiply then, and let's just see what we get. So I get 2 plus 3k squared. So 2 plus 3k, oops, my pen works, there we go. 2 plus 3k squared is equal to k times then 5 plus 4k. Just like that, okay? So feel free to write this as a product of brackets. I'll just do it off the top of your head. I'm going to be lazy and do it off the top of my head, but just be careful, right? Don't make any silly mistakes here. So what do we get then? I get 4. I get 6k and another 6k, so that's 12k and 9k squared. And that is equal to 5k plus 4k squared, right? Like so, okay? So let's just take everything over to one side here. That's 9k squared, so let's just subtract 4k squared and 5k from both sides here. If we do that then, what I get here is 5k squared. That's 4 plus 12, so that's 16. I can't do anything else with that, right? And I've got 5k there, so minus 5k. And then plus 16 here. Have I done that correctly? That's all equal to 0. Let me just double check that. So 5k squared. Have I made a mistake here? Oh, I have made a mistake. I am stupid. As I said before, that should be 12k, right? That is embarrassing. So there we go. I was going to say, what's going on here? Apologies, everyone. I am stupid. So let's try again. So I said, don't make a mistake. And then I went on to make a mistake. So that is embarrassing. So where am I up to here? So 5k squared, yes. 12k minus 5k, that is plus 7k. Yes, that's good. It now looks correct. And plus 4, yes. And that is all equal to 0. Perfect. Okay. We've discovered that I am stupid, but there we go. I can fix the mistake. So let's just consider here the discriminant, right? So now consider delta, which is equal to b squared minus 4ac, right? So what do we get here then for delta? Where delta is a discriminant, right? So b squared, that's 7 squared, minus then 4 times a, which is 5, times c, which is 4. So what do I get here? That's 49. 4 times 4 is 16, times that by 5, I get 80, so minus 80 there. 49 minus 80 is minus 31. Yes, so we get a negative number, which is perfect. That's what we wanted here, right? Because this forms our contradiction here. So what we can say here then is the quadratic has no real solutions, right? Because the discriminant is less than 0. So the quadratic equation, I'll just say the quadratic here, has no real solutions. It has no real solutions. But k, as it is here, it's the first term, right, is given as a real number. So the quadratic has no real solutions, but k is given as a real number. It's given as a real number, and therefore then we have a contradiction. So we have a contradiction. We have a contradiction. We have a contradiction. And in that case, then the sequence does not form, or it does show that this sequence here is not a geometric sequence. And therefore then, the sequence is not a geometric sequence. So apologies, by the way, my handwriting is absolutely shocking, but hopefully you can follow along. Geometric sequence. Just put SEQ there for sequence. Okay. I do always hate proof by contradiction more for kind of like the waffle that you have to put with it. I was never good at English, so I always do struggle a little bit to kind of articulate my thoughts, but hopefully that does make sense what I've put here, and the contradiction that we formed here in the working, right? So there we go then. That gives us the solution to part A. I don't have a ton of room here for part B and part C, and we don't really require the kind of working here of part A for those two parts. What I'm going to quickly do here is just pause the video, clear the screen, then we can continue with part B and part C to finish with, right? So we cleared the screen here, right, as we can see then. So let's just continue with part B and part C here. Now for part B then, what we're told here is the first 3 terms of a different geometric sequence given by the following 3 terms here. So for part B then, what we want to do here is just find the value of k. I've got a problem here. My problem here is that I've got 3 different terms, right, which is all well and good, but the second term here doesn't have the same base as the first term and the third term. They do all need to have the same base here. So let's just rewrite the second term here. We can write this as 2 squared to the power then of 5 minus k. And just using basic index laws here, we get 2 to the power of 10 minus 2k. Okay, so we get 2 to the 10 minus 2k there. So this here is our second term, right? Perfect. So what I can now do here, similar to what we did in part A, right? I can write the second term over the first term being equal to the third term over the second term, right? That does hold for a geometric sequence. So what we've got here then is 2 to the 10 minus 2k all over. So the first term here is 2 to the 2k plus 3. 2k plus 3. like so. And that is equal to then the third term here. So that's 2. So rather than writing this here as 2 bracket 2k plus 1, I'll just expand this just to make life a little bit easier. So that's 2 to the 4k plus 2 all over them. The second term here, which is 2 to the 10 minus 2k. So it's 2 to the 10 minus 2k, just like so. Okay. Now what I can do here then is again just use basic index laws here, right? They all have the same base, so we can just subtract the powers on the left hand side and also the right hand side here. So if we do that then, what do I get here on the left hand side? So I get 2. So for the power here, I've got minus 2k minus another 2k, so that's minus 4k there. And I've got 10 minus 3. Okay, so 10 minus 3 is 7. So I get 2 to the 7 minus 4k there. And that must be equal to them to get 2. And again, just subtract the powers here. So 4k minus minus 2k, so just be very, very careful there. That's 6k. And then I've got 2 minus 10, giving us minus 8. And up to now, this all looks good. So because we've got the same base here, the powers, the exponents must be equal. So what I've got here then is 7 minus 4k is equal to 6k minus 8. Okay. And let's just solve for k here. And then that is part B complete, right? So add 4k to both sides, I get 10k. And add 8 to both sides here. So 7 plus 8 is 15. So 10k is equal to 15. And therefore k is 15 over 10. Therefore k is 3 over 2. Perfect. Okay. And there we go then. So hopefully not too challenging there for part B. And this here is our solution. And then finally for part C here, it just says show that the sum of the first 10 terms of the series is 65,472. Right, so what I've got here is the first 3 terms, but they're in terms of k, right? So just to make my life a little bit easier here, let's just give these as an actual number. So that's 2 to the 2k plus 3. So 2 lots of 3 over 2. So that's going to be 2 to the 3 plus 3. So that's 2 to the 6, which is, so 2 to the 5 is 32. So that's 64, right? We get 64 there. This here then, so that's 2 to the 10 minus 2k. So that's 2 to 10 minus 3. So that's 2 to the 7. So get 2 to the 7 there. And I would expect then this one here to be 2 to the 8. So 2 to the 7 is 128. So what I've got here then is, I've got 64, 128, and then we should expect this one here to be 256, right? So that is, so it was 2 to the 4k plus 2. So 4 lots of 3 over 2. So that's, what is that? So that's, yeah, 2 to the 6 plus 2, which is 8. Perfect. So I'm trying to do this off the top of my head. But there we go. So the first 3 terms here are 64, 128, and 256. So I can see 2 things here. I can see them for this geometric series here, I'll sequence that A is 64. My pen works, there we go. 64. And then for the common ratio here, R, that's just 2, right? 64 times 2 is 128. 128 times 2 is 256. So R is 2. So what I want here is a sum of the first 10 terms, right? Well, don't forget them. The sum of the first n terms here is given as A times 1 minus R to the n all over 1 minus R. Okay? So, for the sum of the first 10 terms here, that's going to be A, which is 64, times 1 minus R, which is 2, to the power then of 10. So I've got 64 bracket 1 minus 2 to the 10, and that is all over 1 minus R, so that's 1 minus 2. So you can just throw this into your calculator here if you want to, and you should get this answer here, hopefully. If we don't, then we've made a big problem somewhere. But if you just quickly simplify this here, what do we get then? So I get 64 bracket 1 minus, so 2 to the 10 is 1024. So 1 minus 1024, that's all over minus 1. And again, just quickly evaluate this here. Get minus 65,472 all over minus 1, which is just simply 65,472. as required, right? That is exactly what we wanted here. So as required. Perfect. Okay. And there we go then. Perfect. Okay. And now we have it. So that gives the solution there to question 11. Now for question 12 here, we have this beauty of a question, right? Absolutely love these questions. They're so fun. No sarcasm. As we can see on the screen, I've got 3 parts to this. I've got part A, which is just dealing with partial fractions, part B on solving differential equations, and then part C is just a quick follow on from part B, right? So as I said, these questions are so fun. They take up so much room, and they're really, really exciting. So let's just begin. I can't wait. So for part A then, as we just said here, we're dealing with partial fractions, right? So we've got this here. So 1 all over x times at minus x. And we want to express this here then in partial fractions. So that will be identical to, or equivalent to here, however you want to describe that. So it'll be identical to a over x. That's the first factor there, right? Plus b then. Plus b all over the second factor here of 18 minus x. Just like that. Okay, like so. Now, what we're going to do here is get the right-hand side over a common denominator. So I would times a by 18 minus x, right? And I would times b by x. At that point there, these here would have the same denominator of x times 8 minus x. So once we do that, the numerators then must be equal as well, right? That's the whole point of doing this here. So I get a times 8 minus x there, plus b then times x, so just bx, right? So plus bx, and this here is equal to, or identical to, we can even say here, to 1, right? Because what we've now done here is got this over a common denominator. And in that case then, if they share the same denominator here, then the numerators must also be equal as well, right? Or equivalent. So what I now want to do here is just substitute 2 values of x in, 1 to eliminate a and 1 to eliminate b. It doesn't matter which one you start with. But I think the easiest to spot here is if we let x be equal to 0. So if I let x be equal to 0 here, we eliminate b and we can solve for a. So we get 80 minus 0 there, which is just 80. So 80a. So 80a is equal to 1. And therefore then a here is equal to 1 over 80. Okay. So that's a. We now need b here. So for b then, I will let x be equal to 80, right? So 80 minus 80 is 0. A times 0 is 0, right? So it eliminates a there. So we let x be equal to 80. So I get then 80b. So 80b is equal to 1. And as you can see then, we get the exact same answer for b as well, right? So b is equal to 1 over 80. Spooky. So to finish with then, what you do need to do here is actually express it in partial fractions. That's the whole point of this question, right? You found a, you found b, but don't forget then to express it in its partial fraction form, its partial fraction decomposition. It would be in posh. So for them, what I've got here is 1 all over x times 80 minus x. And apologies, by the way, I am losing my voice. At the moment, we're going through a mad heat wave and my hay fever is killing me off. So I get this here, which is identical to, so it's a over x, so a is 1 over 80, so I get 1 over 80x. 1 over 80x there, plus then b over 80 minus x, where b then is 1 over 80, so I get 1 all over 80 times then 80 minus x, just like that, right? And there we go. So it is just 2 marks. I kind of lost track of where the marks were, but it is just 2 marks, right, for all of that. It's a little bit painful, but there we go, right? So that's the first part of this question complete. What I'm going to quickly do here is just pause the video, clear the screen, and then we can continue with part B, right? Because for part B, we do need quite a bit of room. So let's quickly pause the video and clear the screen. And just like magic, everything is gone, right? Other than the partial fraction decomposition required in part A. The reason that I've kept that here on the screen is because we will need it for part B as well. I've also got the wrong pen, which is never a good start. Get rid of that. Wash, wash, wash. Right. Part B. So for part B then, we're given all of this information here, quite a bit of waffle, right? So we've got a scientist here who is studying the spread of an oil spill across the surface of a lake. the lake has a surface area of 80 meters squared. So the area of the lake covered by oil, x meters squared, is modeled by this given differential equation here, where t is the time in hours after the start of the study. What we're also given here is that at the start of the study, 4 meters squared of the lake was covered by oil. How depressing. So for part B then, we want to solve the differential equation here, that is this one, to show that x is equal to a over 1 plus b to minus t over 5. 6 marks for this, right? So this is definitely the most challenging part of this question here, which is kind of dictated by the number of marks anyway. There's quite a few kind of different steps going into part B. So as I've already said then, you do require the partial fraction decomposition from part A. So keep that at the back of your mind here. We're going to need to use that a little bit later on. So to begin with here for part B, right, we want to solve this differential equation here. Now, as A-level math students, the only way that you know, I can't speak, the only way that you know how to solve a differential equation here is by separating the variables, right? If you're going to do A-level further maths, there's different ways to solve differential equations. But for A-level maths, the only way that you know here is to separate the variables, right? So what we're going to do here is separate the variables for this differential equation. What I want to do then is get anything in terms of x here on the left-hand side. That's this side here, and then everything else over on the right-hand side, right? So let's just do that then. I've got x times 80 minus x here on the right-hand side. I want that on the left-hand side then. So to get that on the left-hand side here, what we do then is we divide by x times 80 minus x, right? We just divide by whatever we've got here on the right-hand side. This 400 here on the left-hand side, I don't want that. And I don't want the dt. So what I will do here is divide both sides by 400 as well, and times both sides by dt. And once we do that, we should have this in the required form here, right? We will essentially have separated the variables. So let's just do that here. That's enough of the waffling. So on the left-hand side, then what I get here is 1 all over, it's 1 all over x times 80 minus x, just like that, dx. Like so. So this here then is for the left-hand side. Once we separate the variables, we get this here. And now on the right-hand side then, as we just said before, we divide both sides by 400. So I get 1 over 400. And we times both sides by dt. So if you want to, you can write that as dt over 400. But most students prefer to just keep it as 1 over 400 dt, which is absolutely fine, right? So we're going to leave it like that. Now what you notice here then, what you notice here, is this 1 over x times a minus x is what we had in part A, right? So what I can do here then is replace this with its partial fraction decomposition that we obtained in part A. So let's just do that here then underneath. So we've got this here, right? So I've got 1 over 80x is 1 over 80x, like so, plus then it's 1 all over this 80 times then 80 minus x, like so, dx, and this is equal to 1 over 400 dt, just like that, okay? Now, for questions such as this one here, once you separate the variables, what we can now do here is just integrate both sides, right? So what I will do here is just put the integral sign in front of my expressions here, so in front of the left-hand side and in front of the right-hand side. But it will look a little bit neater to kind of write this as a fresh line, but I don't have tons of room. So to save me that, I'm just going to write it here on the same line. So we integrate this here, like so, with respect to x here, and then integrate on the right-hand side as well. Apologies, it is a bit of a kind of squeeze here to fit everything on, but that should hopefully make sense of what we've done there, okay? So we now integrate both sides here. So the right-hand side is obviously much easier to work with, but we'll come back to that in just a second. Let's just go through the left-hand side here. So just go term by term here. So the 1 over 80x here, if you integrate that here with respect to x, then what I simply get here is 1 over 80 ln x, right? I get 1 over 80 ln x there, like so for this part. And then for this bit here, just be careful because it's 80 bracket 80 minus x. So once you integrate that, what I would get there is minus 1 over 80 ln of 80 minus x. Okay, so just be very, very careful there. So minus then. So minus here, as we just said then, 1 over 80. So 1 over 80 ln of 80 minus x. Just like that, right? And then this here, so that's the left-hand side dealt with. We've integrated here with respect to x. And now for the right-hand side then, I've got 1 over 400 integrating there with respect to t. So what do I get there? Well, that's just simply t over 400, right? T over 400. But with the right-hand side here, do not forget the constant of integration, right? We don't have limits on the integral. So plus c then. Just like that, okay? Now, at this point here, I do want to make the working a little bit easier. I've got this 1 over 80 here, minus 1 over 80 here, and that's over 400. So to make my life a lot easier here, what I can just do then is times through by 80, right? So if I do that underneath then, what I get here is ln x. So I get ln x there, times that by 80, I get minus ln of 80 minus x. Minus ln of 80 minus x, like so. And then 80 over 400 is 1 over 5, so that's t over 5 there. That's t over 5. We are technically timesing the c by 80 as well, but 80 times an arbitrary constant is still just an arbitrary constant. So I'll just leave that as plus c there, like so. Okay, and we get this here. Now, what I want then here is to use some kind of initial condition to find the value of c, right? So it's up to you kind of how you go about this here, whether you go straight into substituting t into this now or you times through by 5. It really doesn't matter. But I'll just do it from this point here, just say me do an extra line of working. So where is the initial condition in this question here? Well, because it's a modeling context question here, we kind of have to read through the question and pull that bit of information out. So we're told that the lake has a surface area of 8 meters squared. That doesn't really help me at this point here. This is just telling you what x represents here, so that's all well and good. This is the differential equation. It tells you what t is here. Yep, that's great. But this bit here, this is the important bit. So it says, given that at the start of the study, 4 meters squared of the lake was covered by oil, that is your initial condition. What it's telling you here then is when t is 0, x here is 4. That's what it's telling us here, right? That there is the initial condition or the boundary condition, whatever you want to call it. But it's what we're going to use here, okay? So when t is 0, x then is 4. So just substitute x equals 4 and t equals 0 into this equation here. So what does that give me then? So that gives me, so I'm going to get ln 4 there. Have I done that right? Actually, I want to make life even easier. What I will do here is, so you can do it at this point here, but just make life even easier. I'm going to write this as a single logarithm here. So it's going to be ln of x over 80 minus x here, like so, and that's equal to t over 5 plus c. What I was going to say is you can just substitute in at this point here, so you get ln 4 minus ln of 76 over, so that's equal to 0 plus c. So c is equal to ln 4 minus ln of 76, and then you can write it as a single natural logarithm there. That's fine, but I'll just do it like this here. So it looks a little bit neater. So what I get here then is, so using initial condition, what do we get here then? So using the initial condition here, I just get c on the right-hand side. So therefore c is equal to ln, that's going to be 4 over 80 minus 4, so that's 4 over 76, which is the same as 1 over 19. So c is equal to ln of 1 over 19. Perfect. Okay. So we find the c here. So go back to the equation here and replace c with what we just found here, right? Ln of 1 over 19. So therefore then, what I've got here is ln of x over 80 minus x here is equal to, so it's t over 5. So t over 5 like that, plus c, which is ln, that's ln of 1 over 19 there. Perfect. Okay. We're at 10 minutes as well, just for part B here. Like I said at the beginning of these questions, they're painful, but they are worth quite a few marks, right? So we're getting there now. We're making good progress. We want this here, right, though? So x is equal to a all over 1 plus BE to the minus T over 5. Let's just continue from here. So let's just simplify the right-hand side here. What can we do with this then? So imagine we express T over 5 as E to the T over 5, and we take the natural logarithm of that, okay? Because what I can do then is simplify this here on the right-hand side. That's going to give me then ln. So the left-hand side doesn't change, right? So that's ln of x over 80 minus x, just like that. On the right-hand side here then, as we just said, that becomes e to the t over 5, but we take the natural logarithm of that. So the natural logarithm of e to the t over 5, they cancel out and just get t over 5, but it's just a different way to write this because I want to simplify this basically. So that becomes ln of then, and what I will do here is write this as a single logarithm here as well. So it's a product, right? We're adding these together, so it becomes a product. So I get ln of 1 over 19 e to the t over 5. Just like that, okay? Right, let's keep going. We're getting there. What we want at the very end, right, is just x on its own. So at some point here, we do need to get rid of the natural logarithms. To do that, we exponentiate both sides. We take it as e with this as my power, and e again with this as my power. E to the ln, the inverse of each other, and they just cancel. I just get left with this here, the argument of the natural logarithm, and same again here with this natural logarithm. So we've kind of run out of room, which is slightly frustrating, but we're pretty much there. What I will do here is just quickly get rid of these bits here, just so I've got a little bit more room to kind of continue towards the top. We don't need the partial fraction. Oops, I've already kind of put it on the screen, so that's fine. I was going to say we don't need it anyway, but I'll continue from around here. So if we go up here then, as we just said, exponentiate both sides. So we get x over 80 minus x is equal to 1 over 19 e to the t over 5, like so. What I'm going to do here then is just cross multiply both sides then. So I get 19x on the left-hand side. So 19x here is equal to, so that's 80 minus x times e to the t over 5. Yeah, it's not going to look pretty. So e to the t over 5 times then 80 minus x here. Right, let's just keep going. So obviously what I want to do here is get all of the x's on one side. So let's just expand here on the right-hand side. So I've got 19x, like so. That is equal to 80 e to the t over 5 minus then x e to the t over 5. Apologies, by the way. I will kind of separate this off in just a moment. So I will add x e to the t over 5 to both sides here. We've got 80 e to the t over 5 is equal to 19x plus x e to the t over 5 there, like so. Now on the right-hand side here, factor out an x. We've got 80 e to the t over 5 is equal to x bracket. So I get 19 plus then e to the t over 5, like so. We're nearly there now. And we just want x on its own here, so just divide both sides by this here. And therefore then x here is equal to, so it's 80 e to the t over 5. That is all over then this here, so that's 19 plus e to the t over 5. So 19 plus e to the t over 5. Now, at this point here, you might be thinking, question done or part B done, but be careful because what they've got here is a all over 1 plus b to the minus t over 5. We haven't quite got that here, okay? What I've got then is 80e to the t over 5. So basically, if I just divide top and bottom here by e to the t over 5, we should hopefully get the correct solution here, right? Or the required form, basically. So divide top and bottom here by e to the t over 5, then what I get here is 80 for the numerator. That is all over then. So dividing top and bottom here by e to the t over 5 here, right? So I'll come back to 19 in just a moment. This e to the t over 5 here, that just becomes 1, right? So I get 1 there. Exactly as they've got here as well. So that's, looking good. And then this be to the minus t over 5, right? What's happened there then is that's the 19, but we divide that by e to the t over 5, which is just the same then as 19 e to the minus t over 5. As you can see, I've kind of butchered this question in terms of spacing, but this here is the solution. So I'm going to highlight this in a different color. Let's do it in green. So this here then, this is my final solution. Apologies again. It does take quite a lot of room, and I'm doing this on one small screen, so it's not the easiest. But if I kind of box this off here, just so you can see then the separate lines are working. So something like this here. So this was the start of the question. It works all the way down and then continued from this point here, working down to get this here. So as we can see then, A here is 80 and B is 19. And there we go then. So that's the solution to part B. We still have part C to work for as well. So what I will quickly do here is just clear the screen, and then we can continue with part C to finish with. And finally, to finish with then, we arrive at part C. Again, everything just disappeared other than the solution to part B, because again, we will need the solution to part B to answer part C, right? So for part C then, just a short 2 marker here, it just says, hence find the area of the lake covered by oil 15 hours after the start of the study. So what we need here then is the value of x when t is equal to 15. So x is equal to what when t is equal to 15? Well, all we simply do here then is just substitute t equals 15 into our solution from part B, right? This, the solution to the differential equation, basically. So let's just do that here. So therefore, then x is equal to, so it's 80. So 8 there, all over 1, plus then 19e to the minus t over 5. Well, t is 15, so that's 19 e to the minus 15 over 5. So that's minus 3, right? And 15 over 5 is 3, so 19e to the minus 3. Just throw this here then into your calculator. If you do this correctly, what you should hopefully get here is, and this is 2 free significant figures here, is 41.1, right? So 41.1 meters squared there, given that we're talking about area. So 41.1 meters squared. So that is the area of the lake covered by oil 15 hours after the start of the study. Okay. And there we go. So that gets us the solution to part C and the solution to question 12. Apologies. I do appreciate that this question took like 20 minutes in total. As I said, they're always fun, these questions. I love them so much. But anyway, that's the solution to question 12. So we arrive at the penultimate question here, question 13 then. And we've got quite a bit going on here, right? We've got 4 parts of the question. I've got all this waffle here. So let's just quickly read through the question and let's just see what we're dealing with then for question 13. So what we're told here then is in a heating system, a thermostat dial rotates depending on the difference between the room temperature and a target temperature. Now the angle theta measured in radians here for which the dial rotates is modeled by theta being equal to g of x, where x is the room temperature minus the target temperature measured in degrees Celsius, and g of x here is given as arctan of x. And the model also assumes here that g of x is between minus pi over 2 and pi over 2 there. Right, so for the first part then of this question here, part A, all we want to do then is just sketch the graph of y equals g of x, right? 2 marks here to begin with. Now, to sketch this here, if you're not too sure then what this would look like, right? Then just sketch y equals tan of x here, which should be pretty straightforward for most students. So that's my y-axis, and this here is my x-axis, okay? Then if we're going to sketch y equals tan of x here, I need some vertical asymptotes here, like so. I'm going to get rid of that y there. I'm just going to move it over slightly. So I'll move it over here. Apologies. There we go. Now, as we said, then we've got these 2 asymptotes here. These asymptotes then are given as x equals minus pi over 2 and x equals pi over 2. Okay. So if you sketch then y equals tan of x here, what does that look like? It looks, say, something like this. Something like that, right? I'm not the best artist in the world, but it will do. So that there is y equals tan of x, right? Now, that isn't what we want, right? What we want here is y equals arctan of x. So let me just draw then some more coordinate axes here, because clearly we need another sketch then. That's the y-axis again. And this here is the x-axis, okay? So for y equals arctan of x then, that is just the inverse here of this graph, right? So just reflect this then in the line y equals x here. So you should kind of recognize the general shape. I mean, it's just a sketch, so it doesn't need to be a masterpiece, right? So these asymptotes here, x equals minus pi over 2 and x equals pi over 2, they now become horizontal asymptotes, right? So something like that. And same again here. So this one here at the bottom then, that is y equals minus pi over 2. And this one here at the top then is y equals pi over 2. Okay? And again, all we're doing here then is reflecting this in the line y equals x. If we do this correctly then, we'll get something that looks like the following. Apologies, by the way, my art skills are not the best, but that's not too bad. I will take that. So that there then is y equals arctan of x. Okay? That is y equals g of x there, where g of x is given as arctan of x there. Perfect. So that's the first 2 marks there in the bag. I will take that. My art skills, that's not too bad. Okay? So there we go then. That's the solution to part A. Now for the next part here, it says then, at one point in the experiment, the model gives 4g of x minus 2 minus pi is equal to 0. We want to find the exact value of x. We don't really need exact here. We can just write this as find the value of x. Okay? And I will amend that on the actual paper as well, just in case you do want to download it, then it will just say find the value of x, right? So for part B then, let's just do this underneath here. So 4g of x minus 2 minus pi is equal to 0. So just replace then g here of x minus 2 with the relevant function, right? So replace x here with x minus 2. So what I get is 4 lots of arctan. So 4 lots of arctan of x minus 2, like that, minus pi then is equal to 0. That's just this here, right? But what we want to do then is find the value of x. So to begin with, let's just add pi to both sides here to get 4 arctan of x minus 2 is equal to pi, like so. Divide both sides by 4 then. So arctan here. So arctan of x minus 2 is equal to 1/4 pi or pi over 4, whichever you prefer. Like so. Now, what we want to do here is find the value of x. So I've got arctan here of x minus 2. What I can do here then is take tan of both sides, right? So tan and arctan are the inverse of each other, and they'll just cancel, right? I'll just get left with x minus 2 here. So as we just said, then I get x minus 2 here is equal to tan of pi over 4. And you should be aware then that tan of pi over 4 here is just simply 1. So what I've got here then is x minus 2 is equal to 1. And therefore then x here is equal to 1 plus 2, giving us x equals 3. Perfect. And there we go then. So that gets us the next 3 marks here and the solution to part B. So I don't have a lot of room here. Let's just continue with part C. Hopefully we can kind of just about fit this on. Let's see. So what we're told then is a refined model gives this equation here. So arctan of x minus 3 plus 1 over 4x is equal to 0. This equation has a positive solution, x equals alpha. What we want to then show that alpha is strictly between 6 and 7. I won't do it. I won't say 6, 7, but I'm sure some of you will be doing it anyway. Anyway, let's continue. So for part C then, we're looking at the change of sign, right, over a given interval. So imagine this is f of x here. What I want then is f of 6 here and f of 7. We would hope that 1 is positive and 1 is negative. Okay, so for f of 6, then what I get here is arctan of 6 minus 3 plus 6 over 4, like so. then for f of 7 here, I get arctan of 7 minus 3 plus 7 over 4. Okay. What do we get here then for each one? So I probably should have shifted that down a little bit, but never mind. So f of 6 then, I get minus 0.094. Minus 0.094, which is clearly less than, I can't speak anymore, clearly less than 0. Perfect, so that one's negative. What we do hope here then is f of 7 is greater than 0, right? It's positive, which in this case it is. I get 0.179, so on and so on. And that there is strictly greater than 0. Perfect. So f of x here changes sign between x equals 6 and x equals 7. And it's also continuous then on this interval here, 6, 7, right? So let's just kind of denote that underneath them. So f of x changes sign. It changes sign between x equals 6 and x equals 7. And f of x is continuous. I can never spell this though. Is that correct? Continuous? I hope so. So f of x is continuous on a given interval of 6, 7, like so. Okay. So therefore then, alpha is between 6 and 7. Perfect. Okay. And there we go then. So that's all you need there for part C. And then finally, we have the very last part then of this question here, part D. What we're told here then is the iteration formula x n plus 1 is equal to 12 minus 4 arctan of xn. This can be used to find an approximation for alpha. So it says then, taking x not being equal to 6 here, use the iteration formula to find x1 and x2, giving each answer to 3 decimal places. So we don't have a lot of room then. So what I will do here is just quickly clear the screen, and then we'll continue with part D. So I'll get rid of that, and let's continue then with part D here at the very top, right? So you can do this by hand, or you can just grab a calculator. Either's fine. Just grab a calculator, really. It's pretty quick to just do it using a calculator. Like I said, if you want to do this by hand, that's absolutely fine. So for x1 here, that is equal to, so it's going to be 12 minus 4 lots then of arctan of the previous term, which in this case here is 6, right? As we're told here, x naught is equal to 6. That's 12 minus 4 lots of arctan of 6. Throw this here then into your calculator, and we get 6.377 there, to 3 decimal places, as it wants us to do here. So now for x2 then, I would do 12 minus 4 lots of arctan of this here, so 6.377. Or if you're using a calculator here, you would do 6, store that into the memory, and you would do 12 minus 4 lots of arctan of the answer button. You would just press enter twice, right? Either's fine, but I'll write it in full here. So x2 then is 12 minus 4 lots of arctan of 6.377, like that, right? Again, just throw this here into your calculator, and if you do this correctly, what we get here is 6.339 there. Perfect. Okay, so these here then are the 2 solutions required for part D. And there we go. That gives us the solution to question 13 here, the penultimate question in this paper. And then finally, to finish with here, right, as we can see on the screen then, question 14, the very last question for this video and this mock exam paper, is quite a long one. Again, it's quite a few different parts to this question. I've got all of this waffle here, so it should be another fun question. So let's just begin then with part A, right at the very top here. So for part A then, all we want to do here is express 4 cos theta minus 3 sin theta in this form here, so harmonic form, right? Blah, blah, blah. Give the exact value of R, the value of alpha in radians to 3 decimal places. Right, so to begin with here then, let's just consider the harmonic form, right? So R cos theta plus alpha, okay? So just use your formula book here. I want the compound angle result here of cos of theta plus alpha. So altogether then what I get here is R cos theta cos alpha minus then R sin theta sin alpha. Okay. What we're now going to do here is take this right-hand side and compare that with the original expression. Okay. So if we do that then, what do we get here? So what I can see here then is r cos alpha must be equal to 4. Okay. Just comparing coefficients here. So r cos alpha is equal to 4. And also r sin alpha is equal to 3. Again, as we can see here, comparing to the original expression. Now we need two things here. I need r, and we also need alpha. Well, r is nice and straightforward. So r here is just a straightforward application of Pythagoras. I'm going to do 3 squared plus 4 squared, right? And just take the square root of that. So 3 squared plus 4 squared. Well, this here is a Pythagorean triple. I get root 25, which is just simply 5. So r is equal to 5. And now for alpha, well, what I can do here is take r sin alpha, which is equal to 3, and divide that by r cos alpha, which is equal to 4. And once I do that, I get tan alpha is equal to 3 over 4, right? So tan alpha is equal to 3 over 4. So therefore then, just take tan inverse or arctan for both sides. And alpha here is 0.6 over 4 rads or radians. The little c, whichever you prefer there, to denote radians. So to finish with then, let's actually just express it in this form here. So harmonic form. So therefore then, 4 cos theta minus 3 sine theta is identical to, it's identical to then, so it's r cos of theta plus alpha. So r is 5. We get 5 cos of theta plus then 0.6 for 4. Like so. Okay. And there we go then. So that's the first 3 marks in the bag there for the very last question, question 14. So part A done. What about part B then? So this is where things start to get a little bit grim here because we do have the modeling aspect to the question now, but let's just continue. Let's just see how we get on, right? So what I've got here is a Ferris wheel that rotates at a constant speed about a fixed center c. A passenger sits in a carriage at the edge of the wheel. The vertical height h meters of the passenger above the ground is modeled by the following equation, where t is the time in seconds after the wheel starts moving. So using the model, we want to find the following 2 things here. So for B part 1 then, we just want the maximum height of the passenger above the ground. Now again, this is pretty standard here. Normally the first part is the harmonic form part, and then, you know, the subsequent part, part B normally, it's just based on either the minimum or the maximum using the previous part, right? And that also applies here because, just notice here then, 4 cos of 0.2t minus 3 sine of 0.2t is almost identical to this. The only difference here is the argument, right? Rather than theta here, we now have 0.2t, but that's fine because I can just adapt that. So h here is equal to, so it's going to be 18 plus then this here. But this here is what we had in part A, just a different argument. It's just going to be this here, but replacing theta with 0.2t as they've done here for part B, right? We get 18 plus then 5 cos of, as we just said, 0.2t plus alpha. Okay, like so. Well, what I want here is the maximum height of the passenger above the ground. Well, the maximum height here, that would occur when cos of 0.2t plus alpha is 1. So this here, the maximum value of that is 1. So 5 times 1 is 5. So therefore then, h max here, the maximum height, that is 18 plus 5 times 1, which just gives us 18 plus 5, which is 23, right? And there we go, that's in meters, so 23 meters there. Bosh, perfect, okay? Now for the next part here, B part 2, we now want to find the value of t when this maximum height first occurs, giving your answer to 1 decimal place, right? Well, as we just mentioned then with B part 1 here, what we're looking at is cos of 0.2t plus alpha being equal to 1, right? That's when the maximum height occurs. So for B part 2 then, let's just continue underneath here. As we just said, cos of 0.2t plus alpha, that must be equal to 1. We'll take cos inverse then of both sides, right? So on the left-hand side, I get 0.2t. 0.2t plus alpha. I'm losing my mind. We're nearly there. So 0.2t plus alpha is equal to, so it's cos inverse of 1, which gives us 0. And if you do 2 pi minus 0, I get 2 pi, right? So it just occurs in multiples of 2 pi. So I'm going to write this here as 2 pi, right? I'm just going to take n as 1 here to begin with. Okay, so using n equals 1 here, I get 0.2t plus alpha is equal to 2 pi. And what I want here then is t. So just rearrange and make t the subject here. So 0.2t is equal to 2 pi minus alpha. And then finally here for t, that is 2 pi minus alpha all over then 0.2, right? So what is that? Well, alpha, as we found in part A, is 0.644. So altogether then, what I get here is 2 pi minus then 0.644 all over 0.2. Throw this here then into your calculator, and if you do all of this correctly here then, what we get for t, and what is this to, right? 1 decimal place. So to 1 decimal place then, what we get here is 28.2 seconds. Okay, bosh, there we go. So that gives us the solution to B part 2 and the solution to B overall. And we've just got one more part to go here, but as you can see then, we've run out of room on the screen. So let's just quickly pause the video, clear the screen, then we can finish with part C, right? All right, so to finish with here, then we've cleared the screen, right? Let's just continue then with part C to finish this mock exam paper. We're nearly there now, right? Just one more part to go. So the last bit of waffle here, it just says then, for safety checks, the passenger is considered to be in the low height zone when their height above the ground is less than 15 meters. In a single revolution of the Ferris wheel, the passenger is in the low height zone for a total of t seconds. According to the model, find the value of t, giving your answer to 3 significant figures. And we can't just use our calculator here. Unfortunately, that would be nice, right? But yeah, we need to do it by hand. So for part C then, how do we do this? Well, I've also included here the model again from part B, because we will need to use this here to finish part C, right? Now, you could do this as an inequality here, but I don't recommend doing it as an inequality. Treat this like an equation for now, because what I want here are what we call the boundary times, right? I want to find here the time where we then go under 15 meters and then the time when we come back above 15 meters, right? Because what we're looking for there is the time in between. So let's just start here then by setting this equal to 15, right? So I've got 18 plus 5 cos 0.2t plus alpha is equal to 15. So to begin with here, subtract 18 from both sides. We get 5 cos 0.2t plus alpha is equal to minus 3. Now divide both sides by 5. We get cos of 0.2t plus alpha is equal to minus 3/5, right? Like so, okay? Right, now what I want here is the angle, okay? So what I'm gonna do here is take cos inverse of both sides, okay? So let's just call this angle here beta. Okay, so beta here is equal to, so it's cos inverse, or arc cos, whichever you prefer, they're equivalent though, of minus 3/5. Okay, just throw this here then into your calculator. And what we get here is 2.214, so on and so on. Okay, now the second angle here is going to be 2 pi minus this, right? The second angle is, as we just said then, 2 pi minus this angle here of beta. Okay, so do 2 pi minus this here, so 2.214, throw that into your calculator, and what we should get here is 4.069. Okay, so what I now want here is what we just said, right? It's what we call the boundary times. So for the boundary times here, then we do what we just did in B part 2, right? But rather than using 2 pi here, we use these two angles here. So 2.214 and also 4.069, right? So boundary times. So boundary times here, it will be given as them. So it's t here is equal to, so it's the angle. So we'll start with this one here. It doesn't really matter which one you start with. So 2.214 minus then alpha. So don't forget that in the previous part we had t is equal to 2 pi minus alpha over 0.2. But rather than 2 pi, as we just said then, we use these angles here. So 2.214 minus alpha over 0.2. Perfect. And then for the second one here, it's a second angle. T is equal to this angle here, 4.069 minus alpha again. And again, too many agains. That's over 0.2. Like so. Okay. So we're pretty much there now, right? What I want here is the total time. So the total time here would be t here. So 4.069 minus alpha over 0.2 minus this time here. That would be the total time then in which the passenger is in the low height zone. Okay. So therefore then t here is equal to, so we do 4.069 minus alpha all over 0.2 minus then this here, 2.214 minus alpha all over 0.2. Well, what happens here then is the alphas just cancel because that's minus alpha minus alpha is the same as plus alpha. So they just cancel. And what we get here then is, so I get 4.069 minus 2.214, like so. And that is all over 0.2. Apologies, we're running out of room here. We'll just throw this into your calculator then. And to free SF then, what we get here is 9.27 seconds. Okay. And there we go. We're there. So that was painful. Those last few questions were quite long, given that they were all modeling type questions. And that's usually the case towards the end of the paper, but we're there. We made it. And that gives us the solution then to the very last question for this video, question 14. So if you made it all the way to the very end then, I just want to say, what a legend. Thank you so much for watching. I am hoping that this paper here has helped with your last minute revision then for paper 1. Coming up shortly. Again, if you want to download the paper, head over to our website, AJMaths.co.uk. Alternatively, if you become a member on our channel here, down below, the last tier then, the support tier, we will email you a copy of all of our predicted papers for A-level maths if you drop us an email at support@ajmaths.co.uk. So drop us an email with your YouTube username if you have done so. But I think that's just about it, right? So, of course, best of luck with paper 1 when you come to sit that. And again, I know we'll get a lot of questions about this. Yes, we will be doing a paper 2 and a paper 3 when they're released shortly, or when we release those shortly. I'm going to wait though until paper 1's been sat next week for that. Okay. But yeah, that's enough of the waffling. We got there. I am tired. I'm going to take a big break now. But there we go, right? So again, best of luck with paper 1 and thank you for watching.